Good evening, everyone. Welcome to Byju's Exam Prep IS. First thing, if the audio and video both are fine, please let me know. Good, wonderful. So let's begin with the session. There has been a slight confusion that I know of that on Saturday, many of you could not join the session, and for some reason the notification was not sent, or some problem happened somewhere because of which uh, you did not get the notification. And that's why we, although started the class, we conducted the class for almost 20-25 minutes, and then after that we postponed the class because a lot of you could not come. But I just want to know whether you have seen the recordings of that class or not. The recordings must be available. Have you seen the recording of the class? Audio is echoing. Is that the problem everyone is facing? Because I see two comments here about the audio. Let me just try to refresh the session so that if, let's say, that solves the problem. Is the problem resolved now? Is the problem resolved now? Is audio and video both fine? Some of you are saying yes, some of you are saying no. Let me start a poll for you. I just want to understand whether this is a problem for everyone or somebody, only some of you are facing the problem. Is there a audio problem? A for yes, A for yes, and B for no. Is there an audio problem? Please let me know first because I just need to be sure before we begin. So only some of you are facing the problem, not everyone. Is that the case? Why only with my session? Let me see if there are some issues with the setup of this studio. I have the studio people right outside this studio. Let me just check with them once and let me come back. Give me just 2-3 minutes so that I can be sure about audio and the video. Everyone, can you confirm now if audio and video are fine? I mean, especially the audio. Has the audio been fixed? Oh, thank you. All right. So what I was saying is that on Saturday we did begin the class, but I heard that many of you could not get notified for some reason, and that's why we had to close the class and we did not go for very long. An introduction to nuclear energy is something that we had discussed. Have you gone through the recordings, and is there somebody who has not gone through the recordings and you've not seen what we had discussed on Saturday? A lot of you have not. So let me do something. Let me revise a few things from what we did on Saturday, but I'll still request everyone that please, that small class that we had on Saturday, it was just 20-25 minutes, nothing more than that. Please go through it whenever you can after the class. Please go through it because I discussed some things which are the basics of nuclear energy. We did not really start touching the important topics yet. That is what we had to start, and we did not start that day. But an introduction is what we had discussed. So that's why I'll still suggest that you just go there and look at that recording. But let me just basically let me just revise it for you, that what exactly we had discussed. So what we discussed is that there is something called as nuclear energy, and why we call it as nuclear energy is because this is an energy that we get from inside the nucleus of an atom. This is the energy that is stored inside the nucleus of an atom. That's why it is called as nuclear energy. And now, when we say nuclear energy, how do we know that there is so much of energy or so much of potential that we have inside the nucleus? How exactly do we know that? So, for that, we discussed about what an atom is. And what we understand about an atom is that atom has a structure where you have electrons orbiting all across something called as the nucleus, and inside the nucleus, which is a very small space inside the atom, you have all the protons and neutrons. So we have electrons, protons, and neutrons. So this part, this is a small part at the center of an atom. This part is called as the nucleus. This is called as the nucleus. And inside the nucleus, we have protons and we have neutrons. We have protons and neutrons inside the nucleus, and outside the nucleus we have various orbits in which all these electrons are found. Now overall, when it comes to electrons, protons, and neutrons, and especially the nucleus that contains all the protons and neutrons, this is where all the energy of an atom is stored, and a huge amount of energy is stored. An amount of energy which is way, way, way more than whatever energy coal, petroleum, natural gas, etc., or even solar energy, wind energy, etc., can give. So, compared to all that, an atom, the amount of energy that an atom has is significantly huge, significantly much more than what it has. Now, overall, when it comes to the understanding of electrons, protons, and neutrons, discovery of neutron has been very, very important, because we, at a later stage only, we realized that there is something called as a neutron. Protons and electrons were discovered. Electrons were known, and we knew that there are positive and negative charges, but we did not know of any neutrally charged particles, that there are particles which do not carry any charge. We did not know of that, and this is something that we came to know about at a later stage only. Now when we talk about this discovery of neutron, we have to understand that our understanding of a neutron developed from when we understood about the isotopes of an atom. So where, when we talk about hydrogen, we have hydrogen, deuterium, and tritium. These are the three isotopes of hydrogen, right? These are the three isotopes of hydrogen. All right, these are the isotopes of hydrogen. Now in this particular regard, what we understand is that isotopes of these hydrogen is where we understood that isotopes are formed because there are extra neutrons. If neutrons or extra neutrons were not present, then in that case we wouldn't have anything called as isotopes at all. So that's why we understood that this is an extra uh, particle that we have inside the nucleus. Now, overall, when it comes to the understanding of the energy, that is nuclear energy, one of the most important concept in understanding of nuclear energy has been something called as mass defect. That initially the scientists saw something which was very difficult for them to understand, because they saw that although, let's say if you have any nucleus, if let's say inside the nucleus, suppose that you have a nucleus like this, and inside the nucleus you have one proton, suppose that you have one proton and you have one neutron. All right, let's say you have one proton and one neutron inside a nucleus. Now, if you have only one proton and one neutron, and suppose that the masses of both are 10 grams each, then the mass of this nucleus should be 20 grams, right? Mass of this nucleus should be 20 grams. But what they found was that this was not 20 grams, but this was only 15 grams. They saw that this was less than what it should be. So it was very difficult for them to understand that if you have one proton, you have one neutron, you have only these two inside this nucleus, then how is it that although they both are present, still the total mass is less than what it should be? And this is something that was later established or explained in theory of special relativity by Albert Einstein. All right. And this is where Albert Einstein gave a very famous equation called as E is equal to mc squared. Now, in this E is equal to mc squared, E stands for energy, E stands for energy, M stands for mass, and C stands for speed of light. C stands for speed of light. So E is equal to mc squared. Now, when it comes to E is equal to mc squared, what we understand here is that this is where we understand that energy and mass both are interconvertible. And what Albert Einstein said is that mass should be considered as a form of energy. Now, this is what explained the loss of mass, because loss of mass was not really loss of mass, but rather mass converting into energy. Basically, this was the energy being released if you were trying to bring these two particles together inside a nucleus. So, that was the amount of energy being released. And this energy that was being released was enough. This was an enormous amount of energy. Because even if you look here, why we are saying that it's a huge amount of energy, let's say you have a mass of just 1 kg. Suppose you have a mass of only 1 kg. Then in that case, the energy that you have will be 1 into 3 into 10 to the power of 8 squared, because E is equal to mc squared. C is speed of light, that is 3 into 10 to the power of 8 meters per second. So that's why it comes out to be 9 into 10 to the power of 16 joules of energy. All right, it comes out to be this much. So that's why we understand that 1 kg of mass of an atom could be equivalent to this much amount of energy, just as a basic example. So that's why we understand that okay, this atom is packing a lot of energy, and this is way more than whatever all our conventional sources have, whether it is coal, petroleum, natural gas, or solar energy, wind energy, geothermal energy, biofuels, whatever energy source you think of. Compared to all of them, nuclear energy stands out and has a lot of potential, a way more potential than any other energy source. So this is where we understood that okay, fine, this has a huge amount of energy, and this energy is called as the nuclear binding energy. So nuclear binding energy is the energy with which nucleus binds its particles. Energy with which nucleus binds its particles. So that is called as nuclear binding energy. Now, so, and you can say that for all practical purposes, this nuclear binding energy itself is the nuclear energy that we are speaking of. All right. So, for that's why when we say nuclear binding energy, just think of it as the energy possessed by a nucleus, and that's why this is the nuclear energy that we are going to study in this chapter. Now, coming to the actual discussion, and when it comes to this chapter, there are three important concepts, and everything hovers around these three concepts. One is radioactivity, second is nuclear fission, and third is nuclear fusion. All right, so these are the three basic concepts, these are the most important concepts, and everything that we learn in this chapter will basically be the periphery of these three concepts. So what is radioactivity, what is nuclear fission, and what is nuclear fusion? These are the things that we are going to study in this chapter. So before we move ahead, any questions if you have? Why last class was 1 hour only? Because there were certain issues because of which a lot of students were not able to join the session. That's why we had stopped the session midway. Not even 1 hour, the session actually was half an hour only. Energy required to break the bond. I wouldn't say that it is energy required to break the bond. Why? I'll tell you. Bonds are formed between atoms, right? So for example, let's say when you have an atom of oxygen and atom of hydrogen, they are combining, there is a bond which is formed between hydrogen and oxygen. But here we are talking about going inside the nucleus of an atom. So it's not really about breaking the bond, it's the energy barrier to either enter or to exit the nucleus, either to enter the nucleus or to exit the nucleus, the amount of energy that you need. So that's the energy barrier that we speak of here. So that's why please don't think of it or don't confuse it as a bond. So the mass that got converted into energy is the nuclear energy, Prem, you have asked. So more or less you can say that that is one of the ways in which this is happening, and we'll explore this further in this chapter. How mass is equal to energy? No, Vaibhav, mass is not equal to energy. We are saying that there's an equation that defines the relation between this, and what we are saying is, or as a part of special theory of or theory of special relativity, Einstein said that mass should be considered as a form of energy. Can you please give me the monthly timeline for classes where you say that it is written? I'll check why some of you have not received the timeline, or why this routine was not already with you. I'll check with the team. I'll check with them. I've already asked them to confirm on this and upload it on the app if it's not there already. Why biodiesel production is difficult than bioethanol? Because in biodiesel we have to use the uh, seeds, the oil seeds, and extracting energy from oil seeds is difficult. The productivity of oil seeds is very low, and even as a process, esterification as a process is a complex or more complex process compared to fermentation, and that's why these are the things that lead to less productivity in biodiesel. Is this huge amount of energy found in any atom or only the atom of particular material? It is actually found in all the materials, just that there are some from where extraction is possible. Extraction is not possible in both in most of the cases, but in certain cases extraction is possible. Otherwise, any atom, as you've asked, any atom will have this energy. Does nuclear energy of three types, radioactivity, nuclear fission, and fusion? Yes, Vivek, you're right. That's the case. I've already taken the classes in morning batch. Should I take it again? No, hardly 5-10% difference will be there because I just took it last month. Only the last couple of classes were left in the morning batch. That is where you can come back if you want. Jaswant, you asked why there is always same mass defect of nucleus of different atoms of same element. See, because when it comes to mass defect is dependent on the properties of protons and neutrons. And protons, neutrons, and electrons, whichever atom they belong to, their properties remain the same. Just that their configuration is different. So configuration inside the atoms are different. Otherwise, their properties wherever they are always the same. Did Oppenheimer use this formula to construct nuclear bomb? You can say the basics were there, but the formula in general are way too complex to study here. I have a few questions from the previous section. During the break, you can ask me so that, or maybe after the class, let's say somewhere around 8:20, 25, when we are about to end, I can discuss whatever doubts you have. Right. So let's move on. Now, when it comes to nuclear energy manifests itself in three basic forms. One called as radioactivity, another one called as nuclear fission, and the third one called as nuclear fusion. Now, radioactivity is a natural process where we see that this keeps on happening all the time in a lot of different atoms. So, when it happens, how it happens, that is what we'll first study. And then there is nuclear fission and fusion, which as a process are very different from the process that is radioactivity. So, radioactivity, how we define radioactivity is that any unstable atom or any unstable nucleus rather, any unstable nucleus will undergo fission, sorry, it will undergo a decay, and this decay is called as radioactive decay. Now, unstable nucleus undergoes a decay. Unstable nucleus. Now, when we say that a nucleus is unstable, what is the meaning? Try to understand the meaning. When we say that nucleus is unstable, the meaning is either the number of protons either the number of protons are not equal to the number of neutrons. So either the proton and the neutron numbers are not same, not equal, or one more thing, the second way in which it may happen is when the number of protons is very high. All right. So either the number of protons is very high, or inside the nucleus, that is, if the number of protons is very high, then that creates instability. Or if the number of protons and neutrons inside any given nucleus is not equal, then that also creates instability. So these are two ways in which instability is created. So if there is any nucleus which is unstable, it can undergo radioactivity. All right, that will show radioactivity. Now, in case when you have number of protons being very high, this is where it is called as alpha decay. So alpha decay is when you have number of protons being very high. And if the number of protons and number of neutrons are not equal, then the kind of radioactive decay that happens is called as beta decay. So alpha decay, where we see that something equivalent to helium nucleus will be emitted, and then we have beta decay in which electrons or positrons are emitted. We'll discuss about this. So there are two aspects of instability. Just understand this first. We understood that, okay, we have a nucleus, and inside the nucleus we have protons and neutrons. So inside the when it comes to coming inside the nucleus, we know that these are the two particles here, and if these numbers are equal, if there is a kind of symmetry inside, then they are stable. But if there is no symmetry, then they are unstable. And similarly, if the number of protons is very high, that also creates instability. So let's try to understand these two instabilities one by one. that where is this instability coming from. Now, when we look at radioactivity, first one is called as alpha decay, and in this alpha decay what we are saying is that the mass number of the product nucleus is decreased by 4, and atomic number is decreased by 2. So atomic number decreases by 2 and mass number decreases by 4. So what is atomic number? Atomic number is number of what? What is atomic number? Number of protons. Correct. Atomic number is number of protons. And what is mass number? Can you tell me what is mass number? Neutrons plus protons. Perfect. So this is number of protons plus neutrons. Number of protons plus neutrons. This is called as mass number, right? So you have atomic number and you have mass number. Okay, I have one question, and I see that there are a lot of students who are confused here. If you don't remember, then you would not be confused. But if you remember, you might be confused. That when I say atomic number, can I define atomic number as the number of electrons? Yes or no? Can I define atomic number as number of electrons? So a lot of yeses and a lot of no. Vikram, you have given the perfect answer. Dikshit, you are also correct. So only understand one thing, that atomic number, when we define atomic number is always defined as the number of protons, but it can be said to be equal to number of electrons as well in a neutral atom. Why? Because atoms can lose or gain electrons. So you know that there are charged particles, correct? There are charged particles. For example, let's say when you have H plus, it is a charged hydrogen atom, or when you have O2 minus, you have a charged oxide atom. So you have these ions which are positively or negatively charged. Now positive charge does not mean that you have an extra proton. Positive charge means that there is a deficit of an electron. So if there is a deficit of an electron, then you say that these are charged particles or positively charged particles. And negatively charged particles mean that there are extra electrons. So that's why electrons can be gained or lost. All right, electrons can be gained or lost, but you cannot gain or lose a proton. Proton becomes the most intrinsic property of any given atom, because it's very, very difficult to lose or gain a proton. Only under very exceptional circumstances an atom can lose or gain a proton. Otherwise, they won't. All right. So protons are very lazy. Once they have just come inside this nucleus and they've sat in the nucleus, they'll always remain here. They're not bothered with what's happening outside. They'll always remain inside this nucleus. But with electrons, that's not the case. Electrons can be lost or can be gained. So always remember this. So that's why when you have a neutral atom, all right, when you have a neutral atom, then in that case you can say that number of protons and or atomic number can be said to be number of electrons as well. But when you define it, you will always define atomic number as number of protons. So that's why to avoid any confusion, remember that atomic number is always equal to number of protons. So H plus here would mean that there is an extra, sorry, there is not extra, but rather deficit of electron. And O2 minus would mean that there are extra electrons. I hope that this clears things. So that's why when we define, always define it as number of protons. So now what we are saying is that in alpha decay, the mass number of the product is 4 less than that of the decaying nucleus, while the atomic number is decreased by 2. So, so as you can see that this decreases by 4 and this decreases by 2, right? So that's why this is the decrease that we see. So that's why alpha particle is equivalent to helium nucleus. So how many protons and neutrons in helium nucleus? Can you tell me this? How many protons and how many neutrons? Good, wonderful. So many of you have given the correct answer. Two protons and two neutrons, right? So this 2 denotes atomic number. This 2 denotes atomic number, and this 4 denotes mass number. This 4 denotes mass number, and mass number is number of protons plus neutrons. So that's why since number of protons is 2, number of neutrons also will be 2. That's why 2 plus 2 equal to 4. So alpha decay will happen in these kind of nuclei which are heavy, occurs in heavy nuclei, or when the number of protons is very high. All right, when the number of protons is very high, this is when you will see that alpha decay happens. So that's why we said this, that it is when helium nucleus is emitted and number of protons is very high. So this is when alpha decay happens. Now why it happens, also understand this. The size of an atom, or rather let's say size of a nucleus, does not increase in the same ratio as the number of protons and neutrons are increasing. So it's like a classroom. Suppose that a simple analogy is of a classroom. Suppose that this classroom has a total strength of 100. That, let's say it was an offline class. So suppose that we were sitting at a center and we were conducting an offline class. So then in that case, in an offline class, let's say the seating capacity of the classroom is 100, and right now suppose that there are 80 students in the evening batch. So 80 students will occupy their spaces easily and there will be no commotion as such. But suppose that I also say that, okay, morning batch students also please come and join the same session. Now what happens, suppose that there are 80 students in the morning batch as well and they also come and sit in the same classroom. Then what happens, there are 160 students to be seated and the seating capacity is only 100. What next? It becomes impossible that everyone can sit together. Then what happens? You start fighting, and then you will say that, look, we are the original owners of this classroom, so you people please get out. And then you will start throwing them out. So these people who are being thrown out, these are the extra particles being thrown out of a nucleus, because nucleus size also does not increase in the same ratio as the number of protons and neutrons are increasing. So there comes a time when number of protons and neutrons are too high to all exist at the same time, and over that you have all these protons, and these protons are what, they would repel each other. I'm sure you have read about this. If you remember this, that like charges will repel each other, unlike charges will attract each other. So all these protons are like charges, so they will repel each other. So all these protons will try to get away from each other, right? So that electrostatic force is also there, which is trying to get all these away. Plus there are a lot of these particles which are there in this very congested small space. So ultimately it leads to a lot of particles coming out of the nucleus. So that radioactivity is called as alpha decay, and that's why alpha decay will happen in heavy nuclei, and especially once you cross atomic number of 83, that is bismuth. So once you cross bismuth, this is where you'll see that alpha decay will be seen way more than whatever we were seeing until now. So this is what happens in case of alpha decay. Now in case of beta decay, beta decay can happen in both light and heavy nuclei. can occur in light and heavy nuclei. All right, can occur in light and heavy nuclei and will take place when number of protons is not equal to number of neutrons. So when the number of protons and neutrons are not equal, this is when beta decay happens, and that inequality can be there in uh, low atomic number also and high atomic number also. So that's why it can occur in light elements as well as in heavy elements. In both the elements, both the types of elements, it can actually happen. So now in this particular scenario, when we look at beta decay, so in case of beta decay, if you see, there are two examples that we've taken here, one of carbon 14 and one of carbon 12, carbon 10. Usually carbon that we have, the usual natural carbon is carbon 12. So carbon 12 basically has 6 protons and 6 neutrons. So that's why number of protons and neutrons are equal. There are not a lot of particles, so they can all happily exist, no issues. But then what happens, that in case of carbon 14, in carbon 14, can you tell me how many protons and how many neutrons in carbon 14? How many protons and how many neutrons? 6 and 8, correct? So 6 protons, because number of protons will always remain the same, correct? Because if you change the number of protons, the element itself changes. When you go to 7 protons, it is nitrogen. 8 protons, it is oxygen, correct? So that's when number of protons will remain the same. Number of neutrons can change. So you have 6 protons and 8 neutrons. Now if you need stability, you need this number to be equal. When does this 14 become equal? This is 14. So when does this 14 become equal? When it is 7 plus 7, right? So 7 is nitrogen 14. So nitrogen 14 with 7 protons and 7 neutrons. So that's why in beta decay, we see that to attain this stability, carbon 14 converts into nitrogen 14. So this is exactly what happens in case of beta minus decay. This kind of decay is called as beta minus decay. Although this term beta minus is not that important, just know that this is one kind of beta decay. The second kind of beta decay can happen in carbon 10, for example. Now, when you have carbon 10, how many protons and how many neutrons? How many protons and how many neutrons? 6 and 4. Very good. So you have 6 protons and 4 neutrons. Now, if this 6 and 4 have to be stable, then you have how many protons and how many neutrons? 5 and 5. That makes it stable. So ultimately, this is what's happening here in this case to make it stable. So in this manner, there are these two types of beta decays where you do not have a symmetry between the number of protons and number of neutrons. So wherever you do not have symmetry, this is where these kind of decays will start happening, and this decay here is called as beta decay. Now, one question off topic, I mean, not off topic, but rather something that will not be asked in the examination, that when we say that, okay, from 6 protons, now you have 7 protons, from 8 neutrons, now you have 7 neutrons, where did this extra proton come from? Did we actually gain a proton here? Does this proton comes from somewhere outside the nucleus? No. What happens is, yes, as a lot of you have said, yes, Vibhu, you are correct, that this is where, yeah, Ankush, you are also correct, that this is where a neutron internally converts to a proton. Internally, the properties of neutrons change in a manner that they convert to a proton. So in this scenario, the first scenario, what's happening is that a neutron is getting converted into a proton, and in this scenario, a proton is getting converted into a neutron. So internally, this rearrangement is happening. All right, it's a rearrangement of the configuration. It's not that you are losing or gaining a proton from somewhere. As we just discussed, that losing or gaining the proton can only happen under exceptional conditions. Otherwise, protons will be where they are. They are not bothered about anything. So that's why this is a kind of rearrangement, an internal rearrangement. In one case, protons converting into neutrons, in another case, neutrons converting into protons. So this is what we call as beta decay. These are the two types of beta decay. Now there is another decay which is called as gamma decay. Now this gamma decay generally will accompany any alpha or beta decay. That if alpha decay has happened or beta decay has happened, chances are that gamma decay will also happen. Now gamma decay, you do not lose or gain particles as was the case in the previous two cases. Here you don't lose or gain particles like protons or neutrons, etc. But what you gain or lose is energy. So what happens is that alpha decay or beta decay, whenever they happen, after alpha decay or beta decay, what we observe is that there will be an extra energy that you have in this nucleus. That nucleus, if it should have, let's say, 50 joules of energy, it has 100 joules of energy. So there are 50 extra joules of energy with this nucleus. So that extra energy is lost as gamma decay. That extra energy is lost because they are in an excited state. They have extra energy. They need to calm down. They need to calm down, and to calm down, they need to lose this extra energy. So that extra energy that they lose it as gamma. So that gamma decay or gamma radiations, gamma energy or gamma rays or gamma particles, whatever you call, all these things are nothing but the forms of the same. That extra energy is being lost. Extra energy is being lost so that they can come back to their stable energy state. This is what they are trying, this is what they are doing, and to do that, that extra energy being lost is called as gamma decay. So when nucleus is in an excited state, so excited state means that they have extra energy. They spontaneously decay into ground state. Ground state is the usual amount of energy. Decays into ground state, a photon is emitted with energy equal to the difference between the two levels of the nucleus. This is gamma state. So meaning that you needed this much of energy, you have this much of energy. So the difference between these two levels will be lost as gamma radiations. So the difference will be lost as gamma radiation. So that much amount of energy is of gamma radiations. Now, overall, when it comes to gamma radiations, typically we see that they will be emitted whenever alpha or beta decay results in a daughter nucleus in an excited state. So this is where we'll see that they will come to the ground state by a photon transition, meaning that these photons or gamma radiations are being lost. So gamma decay is this only, that after the alpha or beta decay has happened, you have the nucleus in an excited state, meaning that they have extra energy, and that extra energy is lost as gamma photons, and then they come back to relaxed state. It's just like, let's say, when you have a child and the child, let's say, has a lot of energy, is just jumping around the house, and sometimes some kind of violence helps in bringing them back to their ground energy state. So that bringing them back to the ground energy state is basically gamma radiation or gamma decay. So, but just a side note, I'm against violence, but I'm just giving you an example. So this is basically what we call as gamma decay. So these three are the types of radioactivity, all right? Alpha decay, beta decay, and gamma decay. These are the three ways in which naturally some amount of energy can be lost by a particle or lost by a nucleus. And one can happen when you have a lot of protons inside. One can happen when the number of protons and neutrons are not equal. And the third one will happen when any nucleus has extra energy than it should, or more energy than it should. Right. So any Any question if you have from radioactivity before we move to the next topic? Vaibhav, you have a question? We see how carbon changes to nitrogen in beta decay. So how so does it happen as? Can you rephrase your question? I could not understand your question. What is that daughter cell? Daughter nuclei, basically. Daughter nuclei basically meaning the nucleus that is formed after the after alpha or beta decay. Gamma decay only possible after alpha or beta decay? Not necessarily. It does accompany alpha or beta decay, but at the same time, there are other nuclear processes also that can lead to gamma decay. So it can happen in a lot of ways. For example, even after nuclear fission or fusion, gamma decay can happen. Then Vivek, you have a question. What will happen in case of penultimate electrons in radioactivity? So in case of radioactivity, not a lot is to do with the electrons. So electrons will simply adjust their configuration so that they can attain stability for the entire atom. So there are questions. Please explain again alpha, beta also, and gamma also. So let me just summarize it once again. So what I'm saying is that when you have, let me go back. So when we have any unstable nucleus, it undergoes a decay. Instability comes from either when the number of protons inside the nucleus is very high, or if the number of protons and neutrons, they are not equal. So these are two cases in which you have instability. Now if you have instability, then radioactive decay happens. There are three types of radioactive decay. One called as alpha decay, second called as beta decay, third called as gamma decay. Alpha decay will happen when you have a heavy nucleus, when the number of protons inside this nucleus is way more than it should be. So then in that case, alpha decay happens. And in this alpha decay, you lose an alpha particle, which is equivalent to a helium nucleus. So you basically lose a helium nucleus. And in this case, uh, the the nuclei will try to become a bit more stable. So that's one way. Second way is when the number of protons and neutrons are not equal. So when that's not equal, when there is no symmetry, then in that case also the nucleus is said to be unstable. And in this kind of instability, when you make it stable, to make it stable, the process that happens naturally is called as beta decay, where an internal rearrangement among the protons and neutrons happen in a manner that the number of protons and neutrons become equal. And then you have gamma decay. In gamma decay, the only thing that is happening is that the nucleus is in an excited state, meaning that the nucleus has more energy than it should. So that extra energy that you have in the nucleus, that extra energy is being lost, that extra energy is being taken away as gamma decay. Can you explain the image once again, Prabhjot? Can you tell me which image you are talking about? Then Pavitra, you have asked how to consider plus and minus in beta. So see, a plus and minus is simply based on whether protons are being gained or lost. So when you are gaining a proton, it is beta minus, and when you are losing a proton, it is called as beta plus. How long does carbon 14 exist in its original form? Jaswant, you have asked. So there is a concept called as half-life. So half-life basically is the amount of time that it takes for any radioactive element to come down to half of its original mass. That originally, if it was 100 grams, then how much time does it take to come down to 50 grams? That is called as half-life of radioactive element. Half-life of carbon 14 is 5700 years, almost 5700 years. That is, in 5700 years, 100 grams of carbon 14 would become 50 grams of carbon 14. Then Ankush, you have a question. In case of alpha decay or beta decay, when carbon converted into nitrogen or carbon into boron, how characteristics change? The characteristics basically will be the characteristic of that element. So now, when from carbon 14, when it changes to nitrogen 14, it will have the characteristics of nitrogen. Similarly, carbon 10 will start having characteristics of boron, because it's all about configuration. See, all the characteristics that any element has, it comes from their configuration, the configuration of their arrangement of protons, neutrons, and electrons. So as that changes, this also changes. So as soon as the configuration changes, the properties also change. Then Priyalu, you have a question. Can you tell us some real life applications of radioactivity? We'll discuss this. That's the last part of our chapter where we'll discuss all the different types of applications. What is neutrino? Neutrino will discuss, Manikandan, in the next chapter when we go to space technology tomorrow. We'll discuss about neutrinos. What is positron? Garima, you have asked. So positron basically is said to be an antiparticle of electron. Antiparticle. Antiparticle meaning that it has the same mass and opposite charge. Meaning that it has same mass as an electron, but it has an opposite charge. As electron has -1 charge, positron has a +1 charge. Only shorter wavelength emitted in gamma decay, Vikram, you asked. That's correct. Shortest of the electromagnetic radiations. Then Priyadarshini, you've asked, can you please write the definition of positron in PPT? Positron, okay. So positron basically is an antiparticle of electron, meaning same mass as electron, but opposite charge. Nuclear fusion we'll discuss a bit, maybe after almost 40-45 minutes. Please wait. What is the need of stability and its number, Ketan, you asked? See, stability is something that every system in this universe wants. And you want stability in your life. I want stability in my life. Same happens with atoms and same happens with the nuclei as well. That everything that exists in one way or the other, they try to attain that stability. So it's just about having that configuration that helps them live longer. So that is why stability, and that is what happens in cases of any particles as well in the entire universe. Do we need to know about half-life period? We don't. It's just a data. Isotopes of carbon are present in beta decay. Yes, carbon 14 is an isotope of carbon. Does carbon get converted to another element in beta decay? Yes, exactly. You are correct. Hmm, the rest are repeated questions mostly. Carbon dating we'll discuss later. Beta minus decay, addition of electrons, and beta plus addition of positrons. Yes, you're correct. Positrons and protons both have the same charge, then what is the difference between them? Mass is the difference. Protons are way heavier. Protons are almost 2000 times heavier than electrons and positrons. That's the difference. That's why we don't call protons as the antiparticles, because they are way heavier. Only the charge is same. Anti-neutrino also we'll discuss in space technology. Just wait. Mm, all right. So most of the other questions are repeated questions. All right. So let's move on. The next topic that we have is nuclear fission. Now, when you come across this word fission, what is the meaning of fission? What is the dictionary meaning of fission? Can you tell me this? What is the dictionary meaning of fission? Fission. Yeah, to split, break, divide. Correct. So more or less, as all of you have said, that it is basically splitting or breaking, right? Or dividing. So fission means what? To split, divide, or break, whatever you want. So when we say nuclear fission, this is what is happening in case of nuclear fission as well. Because when we are saying that this is nuclear fission, it simply means that this is where nucleus is dividing into certain parts. So nucleus basically is dividing into two or three particles, and while breaking, all right, while breaking, it releases energy. So what happens is that the nucleus will break, all right, the nucleus will break, and as the nucleus breaks, it releases a lot of energy. That energy is called as nuclear fission. So, nuclear fission is the process whereby an atomic nucleus breaks up into two or more major fragments with the emission of two or three neutrons, and this is accompanied by the release of energy in the form of gamma radiation and the kinetic energy of the emitted particles. So, this is how we understand about nuclear fission, where we are simply saying that you have a nucleus and this nucleus has broken, and as the nucleus has broken, it has released a lot of energy. That's it. Now, coming to this process, that how exactly this process takes place. So, in this particular scenario, if you see this, we have this one uranium, that is uranium 235, uranium which has a mass number of 235. Now, what's special about uranium 235 is that uranium 235 is the only, just remember this, uranium 235 is the only natural element which is capable of undergoing fission. Others can also undergo, but you will have to make them undergo fission. You'll have to create conditions under which they can undergo fission. But uranium 235 is the only natural element or only natural nucleus which is capable of undergoing fission. So what happens is, we take uranium 235, all right, we take uranium 235, and let me also write this up here, it's very very important. So fission occurs spontaneously in the nucleus of uranium 235. So uranium 235 is the only naturally fissile, naturally fissile meaning capable of undergoing fission, capable of undergoing fission. It is the only naturally fissile element. All right. So uranium 235 is the only naturally fissile element. So this is the only element which is naturally capable of undergoing fission. So now what we do in this process, how nuclear fission happens. So you have this uranium 235. Now this uranium 235 is bombarded with a neutron. All right, it is being bombarded with a neutron. So you have this atom of uranium or nucleus of uranium 235, and there is one neutron that you have bombarded towards it. Now as it goes and sticks. This neutron, it goes and sticks to the body of this nucleus. Now, what we see is that this 235 now becomes 236. Why 236? Because an extra neutron has come in. So that's why number of protons remains the same, 92. Number of neutrons change. That's why 235 becomes 236. So now you have uranium 236. Now this uranium 235 is, you can say that it is fairly stable. Obviously not stable in radioactive sense, but it is fairly stable. And uranium 236 is highly unstable. So what happens is that as soon as this becomes uranium 236, it becomes very highly unstable and it breaks. All right, it just breaks. And now as it breaks into two parts. One is krypton and the other one is barium. The other one is barium. So now it has broken into two parts, barium and krypton. Now, while breaking into barium and krypton, it releases a lot of energy. All right, it releases a lot of energy in the form of kinetic energy of the moving particles plus all the gamma radiations. All the gamma radiations. So, this is how we denote gamma. I'll write it here so that you don't confuse. Alpha, beta, and gamma. This is how you denote alpha. This is how you denote beta, and this is how you denote gamma. Right? So alpha, beta, and gamma. So now coming back to this, so what we see is that a huge amount of energy is being released. Now, although a lot of energy is being released, apart from energy being released, there is something else. There are three extra neutrons being released here. Now, these three extra neutrons have a significance. What significance? Understand this. Where are these neutrons coming from? From this reaction itself. Here you had 236, correct? On this side you had 236, which became 92 plus 141. So 92 plus 141 is 233. So you have three more neutrons left. So these are the three neutrons that you have right here. These are the three neutrons that you have right here. So now these three neutrons that you have, these three neutrons that you have, now these three neutrons will go and bombard more of these nuclei. Because when you are doing this experiment, suppose you are doing this experiment, it's not that you are working with only one nucleus. Even if you have just 1 gram of uranium, that 1 gram of uranium will also have immense number of particles, even if you have 1 gram. Do you remember something? I'm going back to your ancient history. Class ninth, you might have studied a concept, or class 10th, you might have studied a concept called as mole concept. Do you remember what mole concept is? Or at least people from the science background, class 11th and 12th, I'm sure you have studied of the mole concept. Anyone who remembers, there is something called as Avogadro number. Avogadro number, right? So Avogadro number, yes, Ankush, you are correct. 6.022 into 10 to the power of 23. So what we know is that when you calculate the gram atomic mass, you know that there are these many particles in 1 gram atomic mass. So just imagine that when we are talking about 1 gram of uranium, then 1 gram of uranium can have up to 10 to the power of 22 such particles. So we are talking about these many particles which are available for these three extra neutrons. So what happens next? That these three extra neutrons will go and bombard. These will go and they will bombard three more of these such nuclei. And from this 3 becomes 9, 9 becomes 27, and this is something that goes on, right? So from 1 it becomes 3, from 3 it becomes 9, from 9 it becomes 27, from 27 it becomes 81, from 81 243, 729. I can go on, but I don't want to. So now what happens? A chain reaction is set up, right? A chain reaction is set up here, and this chain reaction is what we need to control, because if you don't control this chain reaction here, if you don't control the chain reaction, this is what becomes an atom bomb. This is what becomes a nuclear weapon. So if you don't control this chain reaction, it becomes an atom bomb. If you control this chain reaction, you get electricity out of it. So whether you get electricity or whether you create an atom bomb, all depends on whether you control this reaction or not, or whether you know how to control this reaction or not. If you don't know how to control this reaction, it either results into a nuclear accident, or if you have enough amount of energy, then it makes a nuclear weapon. And if you control this energy, then you get electricity out of it. That is why this chain reaction needs to be controlled. This chain reaction that is being set up here in this nuclear fission, it needs to be controlled. And to control this chain reaction, we have a concept which is called as critical mass. We have a concept which is called as critical mass. Now, this critical mass is very, very important, because this critical mass will try to control the number of neutrons, right? If you have to control the chain reaction, you have to control the number of neutrons, because if there are no extra neutrons, extra steps will be controlled. If you don't control the number of neutrons, the reaction cannot be controlled. So that's why there is this concept called as critical mass. In the last 2 months, it has been in the news twice or thrice. If you look at, if you go back to your newspapers in the Hindu, you'll find that there is an article in the month of December, and there is an article in the month of March also, with regards to, not March, February, with regards to critical mass or criticality. Now, critical mass basically is the smallest amount of fissile material needed for each fission reaction to produce at least one more fission reaction on an average. Meaning that critical mass is that mass that you need to attain so that a controlled chain reaction can be set up, or a chain reaction rather can be set up. Now, we neither want to be less than critical mass, nor do we want to be above critical mass. Neither we want to be subcritical, nor do we want to be supercritical. If we are subcritical, meaning that if we have critical mass which is less, all right, if we have critical mass which is less than, let's say if we have the mass which is less than the critical mass, then this reaction stops quickly. If you have less than critical mass, if you have the fissile material having mass that is less than critical mass, then the chain reaction cannot be set up, because you do not have enough neutrons. And if you go above critical mass, then the rate of reaction can very quickly change, and it can go uncontrolled. So neither you want to go above critical mass, nor you want to be less than critical mass. Suppose that critical mass for any reactor, I'm just being very trivial here. Let's say for any reactor, if the critical mass has been defined as 10 kg, 10 kg of uranium, that you need to have 10 kg of uranium for a controlled chain reaction. So then neither you can be 9.9 nor you can be 10.1. You have to be 10. You have to be at 10. So that is critical mass. That is the importance of critical mass. That neither you can be above critical mass nor you can be below critical mass. All right. So below critical mass, below critical mass, there are not enough neutrons to set up a chain reaction. All right. Above critical mass, the chain reaction can go uncontrolled. All right. So above critical mass, the chain reaction can go uncontrolled. Below critical mass, not enough neutrons to set up the chain reaction. So that's why you can neither be below critical mass nor you can be above critical mass. Now, recently the news has been that there is one nuclear reactor that we have, that is Kakrapar 4. So Kakrapar 4 nuclear reactor has reached criticality, I think in the month of December. So reaching criticality means that we have defined the critical mass now, we have attained the critical mass now, and now the commercial operations of the Kakrapar 4 nuclear reactor can now start. That is what we mean by reaching criticality. The word used is criticality. So criticality. So criticality basically point at which commercial operations of a reactor can start. All right. So point at which commercial operations of a reactor can start. This is called as criticality. So that's why criticality was in news, that Kakrapar 4 nuclear reactor has now reached criticality. So that's why this is one very, very important point about reaching criticality for any nuclear reactor. Now, there is one more factor that is very, very important in nuclear fission, and this is a concept regarding enrichment, a concept called as enrichment. Now, what is this concept? Let's try to understand this. Uranium. Uranium is a natural mineral in a manner, you can say. We mine for uranium, correct? Now, the natural uranium that we get basically is a mixture of two components. Uranium is a mixture of two components. One, that is uranium 235, the one that we just discussed, which is used in nuclear fission, and then there is uranium 238, mass number being 238. So we have these two which are mixed together. Wherever we have uranium, uranium basically will be a mixture of uranium 235 and uranium 238, where uranium 235 is only 0.7% and uranium 233 is 99.3%. The problem is uranium 238 is not fissile. Uranium 238 is not fissile. Not fissile. So if it is not fissile, what does it mean? That it does not undergo fission. If you have an extra neutron and if you bombard a neutron to uranium 238, it will simply digest it. It will keep undergoing radioactivity, but nuclear fission will not happen. Nuclear fission only happens in uranium 235. All right, it only happens in uranium 235. So this is the problem, that the one that is usable, that the one that we need is only 0.7%. The one that we don't need has 99.3%. So this is where the problem lies with uranium, or the natural uranium, and this is where we carry out a process which is called as enrichment. So enrichment is a process where we convert some of uranium 238 to uranium 235, and we increase the percentage of uranium 235. So in enrichment, we go from 0.7% of uranium 235 to 3 to 5% of uranium 235. All right. So we what we basically do is that we increase the concentration of uranium 235, or we increase the proportion. Enrichment, in a manner, we can say that it is where we increase the proportion, increase in the proportion of uranium 235. Increase in the proportion of uranium 235. So basically what we mean is that now from 0.7% we want that it becomes up to 3 to 5%. Now the question is, why not 100%? Why only 3 to 5%? When we are converting, convert the whole thing. Why only convert 3 to 5%? Why not convert 100%? Because as you start going beyond 5% conversion, this is where it starts to become unstable. All right, this is where it starts to become unstable. So if you are doing, or it becomes easy to weaponize after 5%, beyond 5%, it becomes easy to weaponize. And this is what we would want, if we want to weaponize. Last year this was in the news that the US claimed that Iran has reached almost 85% 85% enrichment. Have you heard of this? That US was talking about and raising some concerns that Iran has now reached 85% enrichment. Heard of this news? Have you seen this news? Not seen. Some of you have. Good. So this is where US had raised this issue that now Iran has reached this 85% of enrichment. 85% enrichment means that they already have a nuclear weapon, that they have created a nuclear weapon. So that is what it means to enrich. That if the enrichment is done up to 3 to 5%, you produce electricity. Above 5%, you are weaponizing it. So that's why internationally it is accepted that a country is supposed to use nuclear energy for peaceful purposes, and that's why they are not allowed to do enrichment beyond 5%. So that's why 3 to 5% is for electricity. 3 to 5% enrichment. 3 to 5% enrichment is for electricity. Beyond 5% is basically weaponization. Beyond 5% is weaponization. So that's why this enrichment process, to keep control on enrichment, is also very, very crucial. So that's why uranium with abundant amount of uranium 235 is called as enriched uranium. So that's why these two concepts are very central to the understanding of nuclear fission. One, the concept of criticality, and the second, the concept of enrichment, because these two have to be taken care of if you want a long-term energy source to be built as nuclear fission, as a part of nuclear fission. So this is what nuclear fission is. Any questions from nuclear fission before we move forward? Vaibhav, you asked, criticality. Reaching criticality simply means that now the nuclear reactor is ready for operations. Now it can start producing electricity. That is what we mean by reaching criticality. All right. So that's a point at which commercial operations of a reactor can start. That now you can start working or start producing electricity from a reactor. Even thorium can be used. Khushi, you are correct. It can be used. We'll discuss how it can be used when we discuss India's nuclear program later. Then, Deepshika, you asked, is the kinetic energy being stored with the free nucleus to move to another uranium atom? So, kinetic energy is not being stored, but rather the kinetic energy that we produce here is produced as heat energy. And that heat energy will be converted into another form of energy for getting electricity. How that happens, we'll discuss that when we go to nuclear reactors. Which kind is responsible for nuclear fusion? Which kind, Sakshi? I did not get your question. What do you mean by kind here? Jaswant, you was is uranium 238 converted to uranium 235 in enrichment? That is correct. If a country is enriching beyond 5% for nuclear energy, uh, energy welfare, is it not possible? See, it becomes so it becomes so unstable, Ankush, that will not be able to produce energy there. Reaching criticality becomes very difficult once your enrichment has gone beyond that. So that's why we see that after that it simply means that the country is trying nothing but to create a nuclear weapon. Then Vivek, you have asked difference between anti-neutrino and neutrino. See, the difference basically comes not in number of charges as per the charge that electrons carry, but in another case, and that is basically lepton. There are lepton charges that are different between neutrinos and anti-neutrinos. So this is where we see that the change in the charge comes in case of neutrinos and anti-neutrinos. But that's beyond the syllabus of what we are discussing. Critical mass definition not understood. So critical mass definition, just understand this, that critical mass is that mass. Let's say that 10 kg of uranium has been defined as critical mass in any given reactor. Then reaching that 10 kg, or ensuring that we have enough of that 10 kg so that a chain reaction can be set up, that you can keep on going through the chain reaction for a longer duration while supplying that fuel for a long time. Then Shamila, you have asked, could you please tell me how we know that we want to split into 92 and what 141? We don't want to, it happens. It happens naturally. We are not dictating how it happens. It happens naturally. The only thing that we have done is that we have bombarded that uranium 235 with an extra neutron. Apart from that, we are not playing any role. After that, whatever happens, it happens naturally. Enrichment level means nothing but how much of enrichment or how much of conversion you have done. What is the concentration of uranium 235 in your natural uranium? Can we see nucleus? No, we cannot. Nucleus is very, very small. Our eyes cannot see it. What kind is responsible for nuclear fusion? Alpha, beta, or gamma? Oh no, none of the above. None of the above. Fusion is completely different. So alpha, beta, and gamma, they do not lead to fusion or fission. They are different. That's why it said that radioactivity is different, nuclear fission is different, nuclear fusion is different. These are three different ways in which you can get nuclear energy. So that's why alpha, beta, or gamma not related to nuclear fusion. How is it converted? What conversion, Vaibhav, are you talking about? Okay, for enrichment. So for enrichment, basically, just think of how centrifugation happens. So if you know the process of centrifugation, where you try to separate milk from fat, right? So if you want to separate milk from fat, the process that you're using is called as centrifugation. That the one which is heavier will try to settle at the bottom, the lighter ones will be at the sides. So something similar happens in case of separation of uranium 235 and 238. The process very similar to centrifugation is used. Japan was recently in the news with regards to nuclear fusion. That's there in the slides. We'll discuss that later. Just wait for some time. Control measures for a controlled reaction, we'll discuss that when we discuss about the nuclear reactors. We'll discuss that. Why UN is not doing anything against Iran's enrichment policy? See, Iran says that we are using it for peaceful purposes. Iran has not declared that we are creating an atom bomb. It's supposed to be a secret mission. Just that US has been claiming that it's already with them, that they have enriched their uranium. They have been able to enrich and make nuclear weapon. So right now it becomes more of a bilateral issue. That it's an issue between US and Iran, where US has been trying to say this and Iran says otherwise. Anyway, in the presence of US, UN actually doesn't matter, but that's a very different geopolitical story. But it's not that UN has not raised concerns. UN has raised concerns here, but Iran has maintained that they are not making any nuclear weapon. Is fission like love happens naturally? It's more like a breakup that also happens naturally. Then we are confused that nuclear powered energy renewable or non-renewable because simply after finishing all the uranium or thorium deposits will it will finish. That's true in the present sense, but we'll discuss about the future also, and there you'll see that the scenario is quite different. What if we bombard proton to a nucleus? Will be very difficult, first and foremost, because protons are positively charged, and getting that proton to enter inside the nucleus will be very difficult, because naturally configuration of the nucleus will try to uh, let the proton go away, because this entire configuration already is positively charged, heavily positively charged. So in that case, one proton will be very difficult. And secondly, when it comes to neutrons, neutrons actually possess a lot more energy than protons. So that's why their bombardment is easier for us and more fruitful for us. 85 enrichment of uranium 238. No, no, no. When we say enrichment, enrichment is of uranium, not of uranium 238 or uranium 235. It is of uranium. That the percentage of uranium, percentage of uranium 235 is increasing in the mix of uranium and uranium 235 and 238. Hmm. Now, the next topic for us is nuclear fusion. Now, in case of nuclear fusion, what we are saying that fusion basically means what? The dictionary meaning of fusion will be to join. So this is exactly what happens here. That what we see in case of fusion is that there are two hydrogen nuclei which are joining together, which are combining together, right? So joining or combining. That is what fusion in general means. So these two hydrogen nuclei, they are coming together, they are combining together, and while they combine together, they also release enormous amount of energy. And the amount of energy that we get out of nuclear fusion is way more than what we get out of nuclear fission. Just look at the sun, and all the energy that you're getting from the sun is nothing but nuclear fusion. Correct? So nuclear fusion is the source of energy for this entire earth and possibly this entire solar system. So that's the amount of energy that hydrogen packs, and that's why nuclear fusion is a very interesting concept for the scientists, where they have been trying to get a breakthrough in nuclear fusion where they can make it possible at a commercial scale. Experimentally they have succeeded, but commercially they haven't, and we'll discuss that. So nuclear fusion occurs when two lightweight nuclear fuel are combined and they form a nucleus of a heavier element. Now when it comes to nuclear fusion, This is what happens inside the sun. This is what happens inside the sun. So inside the sun, these are the reactions. First, you have two hydrogen nuclei combining. All right. So hydrogen combining makes deuterium. Deuterium is the heavier isotope of hydrogen. So makes deuterium. This deuterium combines with more of hydrogen and it forms helium 3. Now this helium 3 is unstable. Helium 3 is unstable. So this helium 3 combines with more of itself to form helium 4, which is stable, which is the stable form of helium because it has two protons and two neutrons. Happy. And in helium 3, you have two protons and only one neutron. That's why unstable. So this is the entire set of reactions. So ultimately, what's happening is that hydrogen is converting into helium. Hydrogen is converting into helium, and while converting into helium releases an enormous amount of energy, and that's the energy that is called as nuclear fusion. So nuclear fusion reactions produce large amounts of energy, can be created only by the means of extremely intense heat. Now that's why what we see is that these are also called as thermonuclear reactions. Thermonuclear, therm meaning heat. So that's why thermonuclear. Very high temperature nuclear reactions are happening. So that's why these are happening. Now when it comes to nuclear fusion, one thing to understand nuclear fusion is that for nuclear fusion to occur, you need to bring the two nuclei so close that the nuclear forces between them become active and they make them to stick together. Now, in case of nuclear fusion, what we are saying is that these two nuclei have to be brought together. They have to be brought very close. Now, to bring them close is not that easy. To make this reaction happen is not that easy. Because in case of, if you go back to what we discussed in nuclear fission was happening in uranium 235, which has a huge asymmetry, large number of protons and neutrons are also not equal. So all the kinds of problems, right, all the kinds of instability already exists. So to make them react is easy, to get energy from them is easy. That's not the case with hydrogen. Hydrogen has one proton. So inside the nucleus, only one proton. So you are the one who's living in a very big house. You are happy. So in that house of uranium, there were 235 particles living. And in the house of hydrogen, hydrogen lives alone. The proton lives alone. So that's why there is no problem that hydrogen has. There is no instability problem that hydrogen has. So you have to create instability. You have to create this instability, that this person was happily living alone. Now this person is getting married, and by getting married this person is now inviting trouble. So this is basically what happens in case of fusion, that you have to make fusion happen. Fusion will not occur naturally easily as it was the case with fission. So that's why there are very special conditions under which nuclear fusion is possible. So when it comes to these conditions, what are these conditions? Either you have to have extremely high temperature, extremely high temperature, extremely high pressure, or very strong magnetic field. Very strong magnetic field. So these are the conditions that are necessary to attain fusion. Conditions required for fusion. Right. So these are the conditions that you need for fusion to occur. Otherwise, fusion is not possible. So you have to have very extreme conditions, very specific conditions, and only under these conditions nuclear fusion is possible. Under otherwise, it is not. So now in this particular scenario, when it comes to nuclear fusion, there are two approaches that we use. there are two approaches that we use to make fusion possible. One which is called as magnetic confinement, and the second one is called as inertial confinement, right? So one is called as magnetic confinement and the other one is called as inertial confinement. Magnetic confinement is when you are using very strong magnetic fields, right? You are using very strong magnetic fields, and only under these strong magnetic fields you are able to get the conditions right for nuclear fusion to occur. So it uses strong magnetic fields to confine the plasma to create the conditions needed for fusion energy to produce. Now, in this case, when it comes to nuclear fusion, what we need is a magnetic field, a magnetic field which is of toroidal shape. We need toroidal shaped magnetic field. Toroidal shaped magnetic field. So, do you know what is toroidal shape? Do you know what is a toroidal shape? No. Do you know what this shape is? This is the toroidal shape, the shape of a donut, the shape of a medu vada. That is the shape of, that is the toroidal shape. All right. So this is the shape in which we get the magnetic energy from all around, something like this. All right. So you have toroidal shaped magnetic field, which is basically trying to confine the plasma, confine the charged particles, and which are going to undergo fusion. So these toroidal shaped magnetic field has to be produced. So we'll produce these toroidal shaped magnetic fields, and under this condition, we'll see that magnetic fusion is made possible, and this is called as magnetic confinement fusion. So this is the first case of fusion, and if you know about this, for example, uh, this has been in the news. We have been talking about Japan's JT60SA. JT660SA. This is the new fusion plant or fusion reactor that we have in Japan. And this is the first time where we are trying to use fusion for commercial production of nuclear energy. But we still need to see how much we succeed, whether we succeed, and all these things are still to be seen. So that is what we see with regards to the new reactor that we have in Japan. Apart from that, there is something called as ITER, International Thermonuclear Experimental Reactor. Now, this International Thermonuclear Experimental Reactor, or ITER, is basically another nuclear reactor which is going to use magnetic confinement. It is going to use magnetic confinement. It is going to use magnetic confinement to make fusion possible. Right now, this is under construction in France. All right, it is under construction in France and is supposed to be operational perhaps by 2035, or by 2035. By that time, all of you will already be IS officers. So then you will read about nuclear fusion now has become possible, and you will remember me that 10 years back there was a faculty who taught you that there is magnetic confinement that we are using, and this is under construction in France. Now, this ITER, or International Thermonuclear Experimental Reactor, India also is a very, very important part of it. So this is a large scale scientific experiment aims to demonstrate that it is possible to produce commercial energy from fusion. And there are all these nations. It started with Soviet Union, the USA, European Union, and Japan. These were the first four members, and then later India, China, and South Korea also joined, and they also now have become a part of this ITER project. India also is a very, very important part of the project, and some of the parts that we have in the reactor, these are the parts which have been constructed by India. They have been made by India. So that's why it is one way, this is one way in which we are trying to make this fusion, or we are trying to experiment with magnetic confinement for the future of nuclear energy.
Then another way in which nuclear energy can be made possible is inertial confinement. Now, in this case of inertial confinement, we want to use powerful lasers or ion beams. Now, lasers will be used, and with the help of lasers, we'll try to bring the particles together. We'll force the particles together with the help of very powerful lasers. Now, this also has been done, and this is where very significantly it has been in the news for the past 2 years. First in December 2022, and then in August 2023. Fusion could be a clean breakthrough, energy breakthrough, and the US scientists have repeated the fusion power breakthrough for the second time. So we have this lab called as the Lawrence Livermore National Lab, and this is where they have attained a breakthrough. And what this breakthrough is that for the first time, we have been able to produce more energy from nuclear fusion than what we consumed in operation. Until now, this is the problem where we are at with nuclear fusion. That with nuclear fusion, the problem has been that experimentally we have succeeded, and in 1980s itself we have succeeded. So experimentally we have succeeded, but the amount of energy that we have used is more than the amount of energy that we get. So if you have used 100 joules of energy in making the operations run, you are getting 50 joules of energy out of it. Then it doesn't make sense. You need to get that extra energy to be commercially viable, right? So that's why until now that hasn't happened. For the first time, the scientists in US have been able to achieve it, that they were able to produce more energy in the operations than the energy that they consumed. So if you look at this data, that they basically released 3.15 megajoules of energy from 2.05 megajoules of energy, enough energy to boil some kettles of water. That much amount of extra energy. So but extra energy, that's the breakthrough. When we are saying breakthrough and so many breakthroughs, and the scientists now have been saying that it looks like we are very close to getting that nuclear fusion or the success in nuclear fusion, that in the next 20 years you will find that there are scientists who are saying that in the next 20 years nuclear fusion will be possible. So unfortunately, we have been saying these 20 years for a very long time, that in 1980s also we were saying that in next 20 years nuclear fusion will rule the world. And even today we are saying that next 20 years nuclear energy or nuclear fusion will rule the world. But unfortunately, this 20 hasn't become 19 yet. But jokes apart, making memes is easy. Conducting these experiments is not. So obviously, it is taking a lot of effort in making these things possible, and that's why we see that there are efforts all across the world, whether US or Europe or India or China or Russia or Japan. In all these countries, in one way or the other, uh, we have been trying to attain feasibility with fusion. Unfortunately, we have not been able to succeed in a manner where uh, operationally or commercially we can use this energy. But the day we are able to do that, the day we are able to achieve that, this is where we'll start calling nuclear energy as renewable energy, because the amount of energy that we can get from very small amount of hydrogen, the amount of energy that we can get will be huge, and this will be an unending, you can say that, because we'll get it for thousands of years. So that's why practically you can say that it will become renewable energy for us. And once nuclear fusion commercially becomes viable, whenever it does, whenever it becomes viable, the day it becomes viable, this entire this entire topic or this entire chapter of energy will be only about nuclear fusion, and will not have to study about anything else, because nuclear fusion would have taken care of any kind of energy needs that we have. So although right now the discussion on fusion energy or nuclear fusion is not that great, because we often see that media keeps on discussing uh, nuclear energy barely. So fusion right now is not in the discussions, but the day it is will be the day when everything changes. So nuclear fusion will have a lot of advantages, and this is why we are even discussing about nuclear fusion, because it will give us an abundant amount of energy, huge amount of energy, because we have seen the sun. We are trying to replicate that sun at a very, 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 very small scale, but we are trying to replicate that sun. So that's why abundant amount of energy, sustainable amount of energy, no carbon dioxide, no greenhouse gas, etc., no air pollutant for that matter. So that's why clean source of energy. No long lived radioactive waste, because that is one problem that we have with nuclear fission, because you get radioactive elements like uranium, etc., which are bad, which are, or plutonium, which are bad for the environment, and they live for very long. For example, half life of plutonium is 20,000 years, so it will live for 20,000 years easily. So that's why these are very harmful, because they will keep on emitting these radiations like gamma radiations, which are very, very bad for health. So that's why no long lived radioactive waste. In case of nuclear fusion, the waste that we get is tritium water, and tritium water is very unstable, and within seconds it converts into normal water. So that's when no long-lived radioactive waste. Limited risk of proliferation. Proliferation means spread, or in a manner weaponization. That weaponizing the same process is not that easy. In case of nuclear fission, that is possible. We discussed about enrichment, that how you keep saying that we are doing 3 to 5% enrichment, and you do 80% enrichment and make an atom bomb. Iran probably is doing that. India has done it in 1970s itself. We also kept on saying that we are using nuclear energy for peaceful purposes, and we made atom bomb, and we did an experiment also, and we succeeded in that test. So while saying that we are going to use it for peaceful purposes, so that's why these kind of issues are not there with nuclear fusion directly, because it's not that the same process can be used. Even if somebody wants to make a fusion bomb, the process will be very, very different. The same process can't be used. In case of nuclear fission, the problem is that the same process is used in making electricity and in making atom bomb. No risk of meltdown, no risk of nuclear accidents, because you need very extreme conditions. As soon as you don't have these conditions, the reaction stops. And again, that is a problem with nuclear fission, because in nuclear fission, leakages may happen. The reaction may come out of the reactor, the particles may come out of the reactor, and that can be very dangerous. We have seen, for example, the Chernobyl accident. So that's why all these things. And then the cost. Once we make it commercially viable, it will drastically bring down the cost of energy, because then you will be able to get ample amount of energy from these reactors, and that's why commercially it will become very cheap. But all these, again, long way ahead in the future. We need to see when it happens, if it happens. So but it holds all these advantages. Look at this question. Very, very, very easy question. It was asked in your 2016 prelims paper. Please read your question. I'm launching the poll for you. Hmm. Interestingly, a lot of you have given a wrong answer. So 47% of you have marked D, which is the correct answer. But I don't understand this confusion. Let me read the question. India is an important member of International Thermonuclear Experimental Reactor. What is this ITER related to? We just discussed this magnetic confinement, and magnetic confinement is related to what? Fusion. Look at the options. It can use thorium in place of uranium. Does fusion have anything to do with uranium or thorium? This is wrong. It can attain global role in satellite navigation. Completely junk. It can drastically improve the efficiency of its fission reactors. It's not about fission, it's about fusion. It can build fusion reactors for power generation. This is correct. This was an easy question. Please don't confuse in these questions. All right, so let's take a break here. If you have any questions from Fusion, please post all your questions. Once we come back from the break, I'll take all your questions and then we'll move ahead. So right now it is 6:52. Let's be back by 7:05. Welcome back, everyone. First, to start with your questions, if you have any. In case of the sun, which element undergoes nuclear fusion? It's hydrogen. Nuclear fusion, always hydrogen. Always remember this. Nuclear fission, still there are variations, but nuclear fusion, always hydrogen. Uranium is used in nuclear fission. Which element used in nuclear fusion? Just as I told you, it's always hydrogen. Hydrogen is used in nuclear fusion. Is Big Bang theory being challenged? Recently, the James Webb Space Telescope has not disproved. So, Vivek, what has happened here is that they have been able to find a few things that, according to Big Bang theory, is not possible to find. For example, they found a star which probably existed only 65,000 years after the Big Bang. But according to the Big Bang theory, the first star should not exist until 3,80,000 years after the Big Bang. So there are these kind of certain variations that they have found in their observations, and that's what led to this kind of challenging of the Big Bang. But still very early days to say that Big Bang is being challenged. Meltdown, what does it say? Meltdown, the meaning of meltdown is accident, the nuclear accidents. For example, Chernobyl, it's a nuclear accident. Just like we use uranium only for nuclear fission, is it the same case for nuclear fusion? So even in nuclear fission, it's not that we use only uranium. We actually can use plutonium also. We also use uranium 233. We also use thorium there. So there are variations that we use, but in nuclear fusion, it's only hydrogen. Can we generate electricity from all three types of radioactivity? We can't, because their natural radioactivity will release very small amount of energy. So that energy is not enough to generate electricity out of it. Although there are batteries, radioactive batteries that we try to create. We'll discuss as applications where ISRO also is working. Uh, Even China has been working on certain projects. NASA has worked on certain projects. So where nuclear batteries are possible to make using the concepts of radioactivity, but electricity production otherwise is very difficult because not enough energy is produced. Does ITR use only magnetic confinement to make nuclear fusion and not other two ways? That's true. Only magnetic confinement. What is half life? Let's discuss this. We'll discuss this in applications of nuclear technology. Please explain the reaction happening inside the sun once again. So let me just go back. Hmm. So this is the reaction. So initially it starts with hydrogen. So hydrogen, the normal hydrogen combines with more of itself to form heavier hydrogen, that is deuterium. So it forms deuterium. Now this is the first layer of the reaction. Then once deuterium is formed, the deuterium keeps on reacting with hydrogen in its vicinity. There are more hydrogen ions or hydrogen charged particles or plasma of hydrogen in the nearby parts of this deuterium. So this deuterium combines with more of hydrogen, and this is where it converts to helium 3. All right, this is where it creates helium 3. And now helium 3, there are a lot of helium 3 particles being there. So that helium 3 combines with more of helium 3 and ultimately leads to the formation of helium 4. So ultimately what has happened is that hydrogen has converted to helium while releasing a lot of energy. So these are the set of reactions that happen inside the sun. How is that the donut structure is created in magnetic confinement? We create it. We artificially create that structure so that we confine the plasma. Basically, there are two types of magnetism. I mean, not very important for you. There is this toroidal shaped magnetic field, plus there is a polar shaped magnetic field also that we create to confine the plasma. But that's not, I mean, a ring like structure like this also is created like this. So this is also created, and this is also created. So these are the two types of magnetic field lines that exist there. Hmm. Actually, a lot of these questions that you all have asked, unfortunately, if I start answering those questions, there will be no limit to us stopping, because nuclear science is way beyond what we are discussing. What we are discussing is just the surface of what actually happens. How this cylinder is created. So we create these magnetic field lines, and this is under which we see that the magnetic field lines will create the plasma structure, which creates energy or generates energy from there on. Hmm. So coming to nuclear reactors, and especially the nuclear reactors that we are discussing here, it's related to nuclear fission. So don't think that we are talking about fusion at all. We are talking about nuclear fission and how we get energy from nuclear fission. Because today the nuclear reactors that we have, the nuclear reactors that we have in commercial operations, these are all nuclear reactors which are associated with nuclear fission. Now, in case of nuclear fission in this particular scenario, what you need to understand is that overall, in case of nuclear reactors, there are all these parts of a nuclear reactor that finally lead to generation of electricity. How exactly that happens, let's try to understand this. So first you have the core, right? You have the core of the reactor, and this core of the reactor is where all the nuclear fission occurs, all the reaction occurs here. Reaction occurs here, all right, at the core of the reactor. And then you have control rods. Now, why control rods? Because there are chances that extra neutrons will be present here, right? There are extra neutrons that can be present, and we have discussed this, that if you want a controlled chain reaction, you need certain number of neutrons. If the number of neutrons goes above, then it goes beyond criticality, and if the number of neutrons are lesser than what's required, it is less than criticality. So for you to be at criticality, it basically needs control rods. So control rods will control the number of neutrons. They control the number of neutrons. All right. They control the number of neutrons. And then after that, we also have another part inside this reactor, and this is called as a moderator. There is another something which is there with the core, at the core, called as the moderator, and the role of the moderator is to control the speed of neutrons. Moderator basically will try to control the speed of neutrons, and control rods will control the number of neutrons. So that's the basic difference between control rods and moderators, right? So in this particular scenario, apart from that, you also have the reflector. So reflector, in a manner, you can say that it's like the wall. It is like the wall which is trying to ensure that nothing gets out of the reactor. All these particles, all the gamma rays and neutrons and all the energy particles that have been created in this reaction, all these can be confined within the reactor. That's the role of the reflector or the wall, that is trying to ensure that it does not interact with the outside world. Then there is the coolant. And the role of the coolant is to carry the heat or carry the energy from the nuclear reactor to the turbine. So that's why it basically carries the energy, carries or carrier of energy. Right? So it carries the energy from the core to the turbine. Now, in this particular scenario, where we look at this nuclear reactor, These all become very crucial parts of the reactor. So if you just to revise all these things that we discussed, you have the reactor vessel, and this reactor vessel is the one that holds all the other reactor parts. All right, this is what holds all the other reactor parts. And you have the core inside the vessel. Core contains the nuclear fuel, and that's why it is the part of the reactor where fission occurs. This is the part of the reactor where fission occurs. Now, this when it comes to the core, you have the nuclear fuel, or let's say uranium, for example, will be there at the core. Then we have control rods. Now, the role of the control rods, as we discussed, that these basically will absorb free neutrons, and that's why they help in controlling the chain reaction. So, as I told you, that they will control the number of neutrons. All right, all the extra neutrons will be absorbed by the control rods, and these are metal rods. These are metal rods that contain elements such as boron or cadmium. So that's why we say that these are control rods, and they will help in controlling the reaction by controlling the number of the neutrons. Then, as we discussed about moderators, so moderators basically will slow down the neutrons which pass through it. So they control the speed. If you remember, we discussed that they control the moderators will control the speed of the neutrons. So that's why these will be required to control or slow down the neutrons which pass through it. So they'll be made of water or carbon or uh, graphite, etc. is used here. So all these will be used as moderators, because slower neutrons will be able to participate in the reaction more. They participate in a reaction more, and they basically increase the efficiency of this reactor. So that's why for increasing the efficiency we need these moderators. And then we have a coolant, and as we discussed that it conducts heat. So coolant is a substance such as water or carbon dioxide. Sometimes again, liquid sodium is also used in certain cases. So it will absorb energy, carry the energy to the turbine, but at the same time made of a material that does not absorb neutrons. Because already to control the number of neutrons, you have the control rods. So if the coolant also absorbs these neutrons, then in that case the number of neutrons will be lesser than what is required. So that's why you have to ensure that you pick something that can absorb heat well, that can conduct heat well, but at the same time does not lead to these does not absorb, does not easily absorb free neutrons. So this is how exactly all these parts of the nuclear reactors work. Now, when it comes to the nuclear reactors, there are different types of nuclear reactors. Now, what are these different types of nuclear reactors? There are, I mean, again, there are a lot of different, types of nuclear reactors, but there are some nuclear reactors that we are using in India. And what we are discussing here, what we are concerned with, are the ones which are there in India, the ones that are being used by India. So the first one and the most common one that India uses is pressurized heavy water reactor. Now, most of the reactors that we have right now in India, most of these reactors are pressurized heavy water reactors. So that's the most common reactor design, not only in India, but across the world. Across the world, most common reactor design is pressurized heavy water reactor. So where we are using enriched uranium as fuel, and moderator and coolant is heavy water. Now, there are two things here: pressurized heavy water reactors. So what do we mean by pressurized, and what is this heavy water? So these two we have to understand. All right, so we have this kind of a reactor which is called as pressurized heavy water reactor. Now, first thing is, when we say that this is a pressurized heavy water reactor, why pressurized? So pressurized heavy water reactor, as you can, in this particular reactor, what we do is that we use a pressurizer, and this pressurizer will ensure that the reaction basically happens at high pressure. What is the significance of high pressure? Why high pressure? Because when you are at high pressure means that the reaction, or sorry, the water that you have keeps on absorbing heat without converting into steam. Normally what happens, that water boils at 100 degrees Celsius, right? We had discussed this in uh, geothermal energy as well, that normally water will boil at 100 degrees Celsius, but when you have high pressure, water does not boil at 100 degrees Celsius. Even if you are at 150 degrees Celsius, 160 degrees Celsius, 180 degrees Celsius, water still can remain liquid while absorbing heat. So what we do here in this case of pressurized heavy water reactor is that water is maintained at high pressure so that it can keep on absorbing heat without converting into steam. And in this way, we improve its efficiency, which this is something that will improve the efficiency of the reactor. So why pressurized? Because at high pressure, water absorbs heat. Water absorbs heat while remaining liquid, even at higher temperatures, or let's say at temperature higher than its boiling point. So even if you are beyond the boiling point, above the boiling point, yet water remains liquid and still keeps on absorbing heat. So that is basically why pressurized. So that's why pressurized heavy water reactor. And then the second question is, why heavy water? First of all, can you tell me what is heavy water? Any idea? Do you know what is heavy water? What do we mean by heavy water? Anyone who knows what is heavy water? D2O, right? D2O meaning that this is water made of deuterium, right? Deuterium in place of hydrogen is used. So heavy water is D2O. Instead of H2O, it is D2O, heavy water. Now, deuterium. What is the difference between hydrogen and deuterium? Another question for you. What is the difference between hydrogen and deuterium? Mass number. Vaibhav, that's perfect. Vibhu, you are correct. Manikandan, you are correct. Ankush, you are correct. Kumari, you are correct. So the basic difference between hydrogen and deuterium is one extra neutron, not proton. Somebody wrote proton, I'll not take the name, but not proton, because if the number of protons increase, then it's not hydrogen anymore. It becomes helium. One extra neutron. Deuterium has a neutron, hydrogen doesn't have a neutron. Because of this, what happens? Because of this, the chances that this heavy water can absorb neutron from the reactor decreases. Correct? Because it already has an extra neutron. So because it has an extra neutron, it simply means that it will not have the capacity to have extra neutrons or absorb extra neutrons, which could have been a possibility in case of normal water. Because normal water, hydrogen has only doesn't have any neutron. Maybe it will absorb neutrons. So that's why heavy water doesn't absorb neutrons. So absorption of neutrons is pretty less or very difficult in case of heavy water. So that is why we use heavy water. So heavy water, because it doesn't absorb extra neutrons easily, hence suitable as moderator and coolant, right? So that's why it can be used as moderator and coolant, because it doesn't absorb extra neutrons easily. That's why this is a pressurized heavy water reactor, because you are using high pressure and you are using heavy water instead of normal water. So if you look at this reactor design, what you see is that you have all the fuel rods. So these are the fuel elements, the reddish orange color ones. These are made of uranium. Then you have the control rods, you have the pressure tubes which maintain high pressure, and this heavy water will be taken to a steam generator where water is converted, or heavy water is converted into steam. And this steam then goes to the turbine. This steam will go to the turbine. Then from the turbine, this steam goes to the condenser. There is a condenser, and this condenser will convert steam into water, and then liquid water again will be pumped back. So you have a pump here. With the help of this pump, the water will be pumped back into the reactor. So in this manner, there is this entire cycle, and you can see that the cycle is very similar to the line diagram that we had seen earlier. So you do not need to worry about the difficulty level of these diagrams. Just think of that basic diagram that we had seen. The things are still the same. You have the core, you have all the fuel rods here, you have the control rods coming in, and then there is pressure tube that you have all across to maintain high pressure, and then it goes to a steam generator where it converts into steam and goes to the turbine, and then from there on it goes to the condenser, and through the pump it is pumped back to the reactor. So this is basically what exactly we are doing in this reaction. So overall, that's why this is basically what we are doing in a pressurized heavy water reactor. Then the other reactor that India has been using is boiling water reactor. And boiling water reactors were the first reactors that India started using. Before we started switching and started making a lot of pressurized heavy water reactors, the first two Indian reactors were boiling water reactors. And in case of boiling water reactor, we are still using enriched uranium, and moderator and coolant is water, normal water, no heavy water here. Now, in this scenario, because you are not maintaining high pressure, so because you are not maintaining high pressure, as soon as water comes in contact with the heat, converts into steam. So steam is naturally generated here, right? Steam is naturally generated here. So you don't need a steam generator as was the case in pressurized heavy water reactor. So again, the same thing goes to the turbine, goes to the condenser, and through the pump, water is pumped back to the reactor. So overall, as a process, it's an easier process, right? As a process, it's an easier process, straightforward process, but efficiency is not that great. Efficiency of a pressurized heavy water reactor is better. The conversion of energy is better in case of pressurized heavy water reactor compared to the boiling water reactor. But there is a simplicity in the design and implementation in the boiling water reactor. Then we have a very, very important kind of reactor, which is called as fast breeder reactor. Right? This is called as a fast breeder reactor. Now there are two terms. Again, let's just try to break down the words that we have to understand the meaning of this reactor, or what kind of reactor it is. We have a fast breeder reactor. The fast breeder, first term is fast. Why fast? Because the neutrons will be traveling fast. Now, there is something that we were using in the other reactors to control the speed of the neutrons. What was it? What were we using to control the speed of the neutrons? The moderator, right? We were using moderator. So moderator was to control the speed of the reactor, not the control rods. Control rods were controlling the number of neutrons, not the speed of neutrons. To control the speed of neutrons, we have moderators. So if you have neutrons traveling fast, then in that case, what does it mean? There should be absence of moderator, right? There should be absence of moderator. So that's why they don't use moderator, and therefore most of the fission produced are produced by fast neutrons. That's why the word fast, that's why the word fast is being used. Now the second term is breeder. What is breeder? It is a term coming from breeding meaning in a manner reproduction, correct? So now the word breeder is being used because what we see in this particular scenario is that the reactor is able to produce more amount of fissile material than what it consumes in operation. So what it consumes, more than that it is able to produce. What it consumes, it produces more than that, and that's why it is being called as it is being called as a breeder reactor. So that's why the term breeder. So what we see is that in case of this reaction, in case of this reaction, the kind of reactor that we have here, we have a fast breeder reactor, meaning that first there is no moderator being used so that the neutrons are traveling fast, and second, the term breeder, because it is very unique in the manner that it produces more material than material that it consumes. That if it has used 100 grams of uranium, or in this case it is plutonium, using 100 grams of plutonium, it produces 150 grams of plutonium. So you are getting more output than the input that you had given. There can't be anything better than this, right? There can't be anything better than this, that you are uh, whatever you are investing, you are getting much more than that, and it's not depleting at all. So that's why fast breeder reactor. So overall, that's why what we observe is that what we see is that you have fast breeder. So why fast and why breeder? So you have a reactor core which consists of a fissile area surrounded by a fertile area. So fertile basically means that this is where fertile means something which is not naturally fissile but can be made capable of undergoing fission. All right. So fertile is something which is not itself capable, not itself capable of undergoing fission, not itself capable of undergoing fission, but not itself capable of undergoing fission, but can be converted, can be converted into fissile material. All right, can be converted into fissile material. So these kind of material, they are called as fertile material. So we see that there is a fissile area and there is a fertile area, and why we need that fertile area, you will understand that in a few moments. So this is what a fast breeder reactor looks like. No need to be worried, just think of the same line diagram that we had seen, that you have the same core, you have the same control rods, you have the same steam generator that you saw, you have the same turbine, you have the same pump, you have the same condenser, everything is the same. So don't worry about the complexity of this design. You will not have to draw this kind of a picture in your examination. A simple line diagram that we saw as the first image, that's enough. So even if you represent like that, that's enough. So don't worry about the complexity of the pictures that you see here. Every picture basically more or less is doing the same job, but in a different manner. So for example, here you are using sodium. This sodium basically is used as a coolant. This sodium is being used as the coolant. So you have this coolant, and through the heat generator you have the liquid sodium going out, and that is where you are getting your required electricity from. So these are the different types of nuclear reactors that right now India has. Now based on this, we have India's nuclear program. Now before this, again, if you have any doubts, please let me know. Just give me 2 minutes. I'll go offline for 2 minutes. Yeah. Do we need to learn the parts and types of reactors? Yes, you should. Questions have come in the past, and questions can come from here, because all these things that we are discussing as static areas, very often they are in the news also. The control rods, the moderators, etc. These are terms that very often keep coming in the news here and there. Why there is a need to control the speed and number of neutrons in a reactor? To increase the efficiency. What we have observed is that in case of slowly moving neutrons, apart from fast breeder reactor, which has a very different mechanism of working, the other reactors, the boiling water reactors, the pressurized heavy water reactors, etc. These reactors, when the neutron speed is slower, then we are able to control the reaction well, and we are able to increase the efficiency of the reaction. And that's why controlling the speed becomes important. And controlling the number, we already discussed that if you have higher number, then you go above the criticality limit, which is bad, which can lead to uncontrolled chain reaction. And going below the number could mean that you do not have enough neutrons to carry on the reaction, something that we had discussed in enrichment itself. Sun also burns in cylindrical shape, not exactly, it's a spherical shape, but you also have the toroidal shaped magnetic field present there also, all outside the core of the sun. The heat exchanger looks like resistor in that diagram. The heat exchanger looks, oh, it's just a diagram, it's not related to resistor at all. It's just a representation, so please don't confuse. Fertile basically means that this is an area, or this is a material where you have these material which are not naturally fissile. Meaning, for example, let's say something like a thorium, which directly doesn't undergo fission, but you can make them undergo fission. You can prepare them in a manner that they can undergo fission, and we'll discuss about that. How to remember this figure? See, only remember this one figure. Only this one figure that we discussed. That's it. Only this one figure is enough. So please don't go into the details of other figures. That's not really required, because otherwise all these reactors are doing more or less the same thing. So you don't need to be worried about it. So just that if you want, just add the blocks instead of making the entire picture. Even if, let's say, a question sometimes, let's say, in some way or the other, a question comes where there is a scope that you can make the entire diagram. Please don't go into the details and specifics of this diagram. Make blocks. Don't waste time there. You have very limited time in writing an answer. Making this diagram itself can take 10 minutes. Is any question asked in the mains examination based on it? Yes, questions have come. We'll discuss about that, those questions as well. Hmm. So more or less all are repeated questions. It is difficult to digest being a non-science. I understand that, and I agree with you that it's not that easy. The concepts that we are dealing with are very advanced concepts, and only thing that helps here is revision. Multiple revisions only is something that can help, and clearing the doubts whenever you have whatever doubts you have. Clearing those doubts are very, very important. That is the only thing that can help in this case. All right. So now let's come to India's nuclear program. Now, overall, when it comes to India's nuclear program, what we see is that India devised a three-stage nuclear program. three-stage nuclear program. And India's three-stage nuclear program is a very, very essential part of the entire setup of nuclear energy that we have. Very recently, in the Hindu newspaper, there was uh, the interview of the head or the chairman of NPCIL, and in that he also very beautifully has discussed about everything that NPCIL is doing right now, everything that India's nuclear program is headed towards. So a lot of questions were answered. Wonderful interview. You can just go and read through it. Uh, but let me tell you about India's nuclear program. Now, India's nuclear program, basically, there are three stages of India's nuclear program that were devised by Dr. Homi Jahangir Bhabha. And Dr. Bhabha, he has been one of the most important scientists of post-independence India. And he, apart from him, there have been others like Satish Dhawan, Vikram Sarabhai, etc. They also have played a very, very important role in the early development of scientific infrastructure and scientific uh, organizations and institutions in India. And he has been one of the greatest minds to exist in post-independence India. Now, he came up with a plan, and he was a very big supporter of nuclear energy. Just imagine that just after independence also, when India got its independence, uh, 1947, just 2 years after nuclear bombs were dropped in Japan. So it was a time when nobody wanted to talk about nuclear energy at all. Nobody wanted to utter the words nuclear at all. Uh, but he was very strong believer that the only way India can become energy independent or India can attain energy security is through nuclear energy. And that's why India must embark on a journey of nuclear energy as quickly as possible. So he was of this opinion. Nobody agreed with him. Nobody wanted to talk to him about this because everybody was very afraid of talking about nuclear energy at all. Uh, and if India and India, that's why did not take any steps initially with regards to nuclear energy, because even if let's say somebody wanted, it would be hugely opposed in the parliament, not only by the opposition but also by the people within the Congress, were not the supporters of nuclear energy at all. Because everybody, when nuclear energy, as soon as somebody thought of nuclear energy, the first thing that could they could think of was nuclear weapon or atom bomb, and everybody now was aware that atom bomb could be made using nuclear energy. So that's why everybody took precautions, and nobody really wanted to create any controversy, because we were a nascent nation. We just came out of the British. Uh, so what at this point of time, what we see is that not a lot happened with nuclear energy, but then we see that some advancements happen. We start getting close to Soviet Union, and the Soviet Union starts helping us in making our own nuclear program. And this is where nuclear reactors are now made, and all these nuclear reactors, the boiling water reactors, the first ones that we started making, all these were thanks to Soviet Union, because Soviet Union was helping us. Now at this point of time, because whether it is boiling water reactor or pressurized heavy water reactor, all these reactors need uranium. India has very limited amount of uranium. There are few uranium mines in India, but they are not enough, and we import a lot of uranium. Now this is where, if we wanted energy security, we had to move away from uh, uranium. And this is where the alternative for us was thorium. Now, thorium, thankfully, India has a lot of thorium. The monazite sand in the southern parts of India, especially in Kerala, uh, has a lot of thorium reserves. And because India, I mean, when you look at the amount of thorium reserves, India is among the top nations in the world. Some of the data will tell you among the top two nations. Some of the data will tell you among the top five nations. I'll want to believe top two. But India, whether top two or top five or top 10 doesn't matter, but India has a huge amount of thorium reserves. Now, we knew that, and this is where Dr. Homi Jahangir Bhabha came up with a plan that we will start making stages in which ultimately by the time we reach the third stage, we will become energy independent, we will become energy secured, because then we will not be dependent on anyone for getting uranium. We will be able to uh, get energy using thorium. So that entire plan that he made was so that we can start using thorium instead of uranium and become energy independent. And this device is something, this entire plan is something that he made in 1960s itself. And he was very aggressive, and he was a supporter of nuclear energy and very aggressive with how India should go into the future with nuclear energy. Unfortunately, he did not live for very long. He died in a crash, a crash where also a lot of controversies happened. In some reports, it is also believed that this crash did not happen just because of some kind of malfunction, but it was a created malfunction. And the Central Intelligence Agency of the US, that is the CIA of US, they might have been behind this crash because they had seen how fast he was moving. They did not like that a nation which just got its independence 20 years back is trying to move so quickly, that now it is talking about nuclear energy. What if today, tomorrow, we also become a uh, nuclear nation with nuclear weapons, and then we start becoming a competition in the international arena? And that is where you will see that US also started supporting Pakistan, started supporting China at this point, so that they can counter India. That India was becoming a powerful nation, India was getting close to the Soviet Union, so they wanted that they should counter India with Pakistan and China. They started creating Pakistan and China against India in 1960s. So today, I mean, unfortunately, this has been the case. Even when they knew what kind of nation Pakistan is, even if they knew what kind of nation China is, it didn't matter to them, only because we were close to the Soviet Union, and they did not want another energy or another power coming up in Asia. So to control the powers that India would perhaps yield, they started creating nations like Pakistan and China. So unfortunately, this is how US always has behaved in the world arena. They do not want any other superpower. You always know how there is a friction between Russia and the US, and right now Iran and the US. Before this, Afghanistan and US, and Iraq and US, and now China and US. Before that, during World War, Japan and US, Germany and US. So unfortunately, this is how always the case has been, and this is where they started seeing India also as a threat, and this is where they started creating Pakistan and China against India. So unfortunately, I mean, these are stories, and we do not really know uh, whether they are completely true or not. But there are stories that this death, unfortunate, untimely death, was because of there was some role of CIA in this death as well. But he devised this plan, and this three-stage plan is something like this: that first, in the first stage, we use pressurized heavy water reactors. We use pressurized heavy water reactors, and with the help of these reactors, we are able to create enough energy that can last for at least 30 years. We have to keep going through the process where we are using uranium in our pressurized heavy water reactors, and we get this Pu means plutonium, right? This Pu means plutonium. So we get a lot of plutonium. Now, why we need to use a lot, why we need to use pressurized heavy water reactors is so that we can get plutonium. Why is plutonium important? Because plutonium is the fuel for the fast breeder reactors. Plutonium is the fuel for the fast breeder reactors. So plutonium is the input, plutonium is the output. If you remember, we discussed that it's a breeder reactor, meaning that whatever is the material that you are using as fuel, you get more of that material. So this also has to be functional for 30 more years so that you get enough of this reaction. Now, another question could have been, why do we need pressurized heavy water reactors to get plutonium for fast breeder reactors? Just think of it. I know it can be complex. Why do we need pressurized heavy water reactors? Can we not get plutonium from somewhere else? The answer is no. Plutonium, gets created in these kind of reactions. Uranium, we are mining, right? We are mining uranium and using that uranium. Plutonium is not naturally present. Plutonium gets created in these kind of reactions. All right. So these reactions that you have here on your screen, these reactions create plutonium. So that's why we need that first stage, so that we can create enough of plutonium so that we can run our second stage with the fast breeder reactors. And this is where you have the fertile. If you remember, we discussed that you have a fissile area and a fertile area. All right, so you have the fissile and the fertile area. So now what happens is that fissile area is for plutonium, and fertile area is for thorium. So thorium basically is fertile here. Thorium is fertile. We have, I'll write here, we have fertile thorium, and this gets converted to uranium 233. This gets converted into uranium 233, and this uranium 233 basically, uranium 233 is what we use in the third stage. Now uranium 233 also is artificial. It also gets created in these kind of reactions. Otherwise uranium 233 is not natural. If you remember, we discussed that natural uranium is uranium 235 plus uranium 238, right? Uranium 235 plus uranium 238. So to get enough of uranium 233, we need thorium. Thorium gets converted into uranium 233 in fast breeder reactors. And then ultimately in the third stage, we will start using thorium based reactors, which can be operational for more than easily 500 years. So 30 years in stage 1 plus 30 years in stage 2 will be equal to 500 years or more in stage 3, where we will start using thorium. You already have a breeder reactor. You'll keep on getting more of uranium 233. You keep on using it for eternity. And eternity here meaning next 500 years or so easily. So that is how these three stages were designed. That is what he had in mind while designing these three stages, so that ultimately we will become energy independent. So this is where we are right now. And but currently we are running behind schedule in a manner, I would say, because largely we are still using stage 1. We are still using pressurized heavy water reactors and fast breeder reactors. We have one fast breeder reactor called as fast breeder test reactor, and there is the second fast breeder reactor that is under construction right now, called as the prototype fast breeder reactor. So we have the fast breeder test reactor, fast breeder test reactor. This is operational. This is operational. And then we have prototype prototype fast breeder reactor, which is under construction. All right, this is under construction. So fast breeder test reactor and prototype fast breeder reactors, these are the two reactors. So prototype fast breeder reactor has been under construction, although it is believed that construction has been completed, but there are certain safety concerns that the scientists are trying to solve as of now. So this is where we are right now. And in stage 3, the kind of reactors that we are going to use are going to be called as advanced heavy water reactors. Advanced heavy water reactors. Now even these are under construction right now. These are under construction right now, and these will be used in stage 3. Whenever we are ready for stage 3, advanced heavy water reactors will be used. Now even if you want, there are Uh, if you go to Bark website, the prototype design for advanced heavy water reactors are also available. You can simply do a Google search, do a Google image search, and look at the reactor design. You will understand why I am not discussing the reactor design here. It's too complex to be taught and too complex to be asked even. But if you are interested, just go on Google, type advanced heavy water reactor, look at the images. Hmm. So, any question from here? What is the role of plutonium? Plutonium, the role of plutonium is that you use plutonium in the fast breeder reactors. Fast breeder reactors need plutonium as their fuel. So, that is why plutonium. Last statement not understood 30, 3500. So, what I'm saying is that if you use 30, first we have to use stage 1 at least for 30 years so that you get enough of plutonium. Then we have to use once we have enough of plutonium, this will help us run the second stage. Then we have to run the second stage for 30 years more, and this is where you'll be able to get enough of plutonium, or enough of rather uranium 233 for the third stage. So 30 years of stage 1, then 30 years of stage 2, then you have enough of uranium 233 to run stage 3. Can you please give us some suggestions to crack UPSC? Ugh, it's not a 1 minute discussion, unfortunately. It needs. How do I explain this in 1 2 minutes? I am really clueless how to prepare. See, it depends. I mean, if you are talking about prelims 2024, then in that case, right now we are in March, meaning that this is revision time. And this means that this is the time when you start closing the subjects. Whatever you have completed, whatever classes have been done, whatever you have read, all these things have to be revised well. This is the time when you do that. Plus, start solving a lot of questions. Questions from the prelims prelims test series, for example, or any question bank that you have. You have to solve all these questions. You have to start doing that, start revising by looking at these questions. Revision should not be blank revisions, it should be targeted revisions. It should be based on all the notes that you have, it should be based on all the things that you've been taught. And then you have to go chapter by chapter, not giving extra preference or no preference to anything, without thinking of what is important and what is not important, what has come in the last year, what can come in this year. Without thinking all of that, everything that you've been taught, subject by subject, start closing it. That's very, very important, because unfortunately what happens is that we keep a lot of things open until the last day, and that is very counterproductive. Don't do that. Start closing the subjects. Maybe you are not, even if, let's say, suppose you think that you will not be able to close every subject, that's fine, but at least the ones that you will be able to close, you should be confident about them. So that is one thing that you need to do, start doing now. Difficult chapter, yeah, I agree that this is not easiest of the chapters, but especially not this chapter, but rather this part of this energy chapter. Nuclear technology is a bit more complex than others. When the webinars of history optional, that we are in touch with the faculty who will very soon start taking history options, and we will announce it as quickly as possible. How many years would it take for India to completely shift to stage 2? See, we will never completely shift to stage 2, because even if we start the operations of stage 2, we will still keep producing more energy from stage 1. As long as these are operational, and we have a lot of plans. Now, we are also making modular reactors, small reactors that will keep on producing more energy. in stage 1. So stage 1 will remain operational, all right, while stage 2 also becomes operational. India's nuclear program still operational? Yeah, it is operational. It is operational. Of course, it is operational. Distraction बहुत होता है study के time. Yeah, there are distractions, and you'll have to find the distractions and kill the distractions. Whether it is your phone, whether it is television, or any XYZ thing. By killing, I do not mean that if it's a person you do that. By killing, I mean that whatever distractions you have to find what distracts you from studying, and you have to find ways in which you can uh, get rid of it. And especially when it comes to the distractions, if let's say if sometimes it can be things as simple as boredom, that you think that I've studied the same thing so many times, I'm bored, or maybe I don't like this subject, so I'm bored. Doesn't matter whether you are bored or not, doesn't matter. You have to mix and match. Maybe that if let's say you feel that you get distracted because this is a subject that you are not comfortable with, or you don't like that subject, then in that case maybe smaller chunks of that subject can be done. That instead of giving 4 hours or 5 hours to that subject, give 1 hour a day, and give the other time, and maybe start mixing the time between all these subjects. But what you have to do, you have to do what the syllabus is the syllabus. You can't get rid of that syllabus. So whether you like it or not, it doesn't really matter. You have to be smart about it. Which state uh, we have reached? State, basically, I mean, as we just discussed, that we still are in stage 1 largely, but we do have one reactor, that is a fast breeder test reactor, which is already operational. What is ACP and DCP? ACP and DCP. ACP stands, if in terms of police you are asking, then it is Assistant Commissioner of Police, and then you have Deputy Commissioner of Police. This is what you have as ACP and DCP. But way beyond what we are discussing right now. YouTube channel, YouTube video by Rohit sir in Baiju's Eyes YouTube channel on how to prepare. Yeah, actually, there is a couple of weeks back he had taken a session on that, so that also can be referred to. Overthinking, yeah, overthinking actually becomes a problem for a lot of candidates. But I mean, you have to be very robotic about this. You have to be very robotic about it. That okay, this is what needs to be done. Okay, this is what I'll do. That's it. Uh, you don't need always. You don't need to find flavors in everything. You know that this needs to be done, so it needs to be done. That's it. So I understand that we start planning and over planning a lot of things also while preparing. But just be as objective as possible while doing anything, and forget about the results. Process is more important. So if you are following the process, if you are in the process, you will get good results. What do we do for current affairs? I attend the Daily Hindu, monthly magazines and webinars. Is it enough? Yes, it is more than enough. That's wonderful. If you are able to do all that, it's great. The target year is 2026. What do we do daily to crack UPSC in single attempt? See, the very first thing is completion of the syllabus. That right now you are attending the class, ensure that you complete the syllabus, and then you start revising, then you start writing answers, then you start practicing a lot of questions, you start adding a lot of current affairs, and meanwhile, doing all that, prepare for your optional subject. Make sure that you are prepared with the optional subject as quickly as possible so that you give it a lot of time before the mains examination. My UPSC journey, my UPSC preparation ended a lot of almost 11 years back. Back in 2013 is when I last went. I mean, I cleared the two stages, did not clear the third stage, and the I can tell you about mistakes. I actually talk about one mistake that I know I did in during my preparation journey, and this was the selection of the optional subject. That I initially started with mathematics optional, and I was good. I wouldn't say that I was not good with mathematics optional, but then I changed the optional subject uh, in peer pressure because a lot of my friends and everyone I was preparing with everyone had chosen sociology. A lot of my colleagues had chosen sociology. My friends in college, they had chosen sociology. So, and sociology had become a popular subject back then, and a lot of people had started switching to sociology. From geography, from different subjects, people had started switching to sociology, and I also switched to sociology. Unfortunately, it was not a subject for me, uh, which is where I tanked sociology in the mains examination. And that is what I believe was my mistake, that instead of believing in what I was strong with, I went with something that was suggested, that my friend suggested, and succumbed to that pressure. That every day somebody will come and tell you that how do you dare think of mathematics as an optional. And this is where we changed the optional subject, and probably should not have been changed, but it is something that happened long time back. Yeah, for 2026-27, the strategy more or less remains the same. What I discussed, the basic objective will remain the same. All right. No, so I am not saying that somebody who's taken sociology is a mistake. Sociology is one of the best performing subjects and one of the highest scoring subjects. I'm saying it was not for me. I'm saying that it was not for me. That's it. Hmm. I've given just one attempt only. I gave an attempt in 2013. That's it. I could not because of n number of reasons. So that's why I could not proceed further. All right. So let's come to our last topic that we have, and the last topic is applications of nuclear technology. Now, applications of nuclear technology first is about all the agricultural applications. Now, we know one very, very important application, and that is electricity. Whether electricity through nuclear fission or whether electricity through nuclear fusion. But electricity is, for me, the most important application of nuclear technology. But apart from electricity, whether electricity through nuclear fission or the future where we are talking about nuclear fusion, whether fission or fusion, electricity is the most important application. But then after that, when we look at all the other application areas, we have agricultural applications. So in agricultural applications, we have water and soil management, pest control, animals productivity, food safety. In all these cases, we actually are able to use nuclear energy, and especially we are making the use of radiations, or rather I would say controlled radiations. Controlled radiations are used in most of these cases. All right, controlled radiations are used. Now when we say controlled radiations, it means that, for example, gamma radiations. So controlled amount of gamma radiations are used in killing the pests. in killing the pests, or in also modifying genes, in making some kind of genetic modification, in all these cases bringing in mutations in the agricultural crops. So we are able to do all that with the help of controlled amount of radiations. Similarly, we also have nuclear fertilizers. We also have nuclear fertilizers. So for example, we have nitrogen 15. So nitrogen 15 is a nuclear fertilizer which helps us in understanding the optimum fertilizer optimum fertilizer for crops. That how much fertilizers to be used, whether 10 grams are enough, or do we use 20 grams, or do we use 30 grams to optimize that. Nitrogen 15 is very very important, because when you are using less, it means that you are not giving enough food to these crops. If you are using more, then it can degrade the soil quality. So that's why finding that optimum amount to be used in agriculture is very very important, and this is where nitrogen 15 becomes crucial. Similarly, in carbon dating, carbon 14 is specifically used to accurately date the historical artifact, to find out the age of historical artifact. And anything that is up to 50,000 to 60,000 years old, we are able to use carbon 14 there. And there is a calculation that we do, because for anything that is organic, anything, plants, animals, other, let's say humans or microorganisms or anything, so any organic form would have carbon in it. All right. And when any organism is alive, just remember this, when any organism is alive, the ratio of carbon 12 to carbon 14 is fixed. All right. Ratio of carbon 12 to carbon 14 is fixed. And when this organism dies, new carbon 12 is not added. So carbon 12 now remains fixed in its amount. But carbon 14 is radioactive. So it keeps on decreasing now. So this ratio starts changing. Until now, the ratio was constant. Now the ratio starts changing, because now the animal is dead, and now, or organism is dead, and new carbon 12 is not formed. So carbon 12 now is fixed, carbon 14 keeps on decreasing. How much carbon 14 has decreased can be calculated. And this can be calculated with the concept of what we discussed as half life. So time period, half life is the time period in which a material radioactive material decreases to half of its original mass. So originally, if it was 50 grams, then now it has become 20 grams for 25 grams, and it will keep on decreasing like that. So for example, in carbon 14, the half life is of 5700 years. So in 5700 years, what happens is that if you have 100 grams, then it becomes 50 grams. If you have 50, 50 becomes 25. In another 57, so in 5700 years, this will happen. Similarly, another 5700 years, 50 will decrease to 25. Another 5700 years, it will decrease to 12.5 grams. Another 5700 years, 6.25 grams. So in this manner, it will keep on decreasing in this particular ratio. So this is how we calculate that how much decrease of carbon 14 has happened, will give us an idea about what should be the age of this historic artifact. Then in industrial applications also, we use ionizing radiations, and this is something that can be used in a lot of different industrial methods. Rather, we do the test of strength of material, strength of different types of material, whether metals or ceramics or non-metals or composite materials, any kind of materials. In all these materials, we can actually make the use of radiations to do the strength testing. So for example, this is what we do in non-destructive testing. that we find the strength of the material. Similarly, enhancing the strength of the material or enhancing the quality of the material can be also done with the help of these radiations. So that's why we see that there are various ways in which in industries also we are able to make the use of nuclear technology. Similarly, in medical applications, in case of medical applications, we can make the use of these radiations. For example, if you've heard of uh, the radiotherapy or chemotherapy that we do for cancer, that cancerous cells are killed with the help of these radiations. So nuclear technology becomes very useful in killing the cancer cells as well. And then lastly, in case of space explorations as well, there is something called as radioisotope thermoelectric generator, and this is something that ISRO has started developing. Now, this is something that is like a nuclear powered battery. All right, nuclear powered battery where we are using the isotope of plutonium 238, and with the help of plutonium 238, we are creating nuclear batteries. So that's why here also we see the application of nuclear technology. So in this manner, we see that nuclear technology can be useful in all these cases, not only generation of electricity or not only creating weapons of mass destruction, but there are a lot of ways. Now, what I'll do for you is, and this is something that can be important from prelims perspective, that there is a list of radioactive elements and their uses. That what element, what radioactive element is used in what, for what purpose. So I've made a list of almost 20 such uses, and that is something that factually can be important for your prelims examination. So I have asked the team to send those documents along with the annotated ppts and the additional reading material. So please go through that, please go through that list of radioactive elements and the uses, so that you can understand what radioactive element is used where. I've only made the list of the ones which are important. Otherwise, there are a lot of them. You don't need to know about everyone. Just the ones which are important. I've made a list and I've given it. So please make sure that you just go through it once. All right. Now let's stop here. We'll discuss about the questions that have come in the mains examination from the energy chapter. This is where we'll start from tomorrow. So we'll discuss about these questions, and then we'll start with our next chapter, a very and probably the most important chapter, that is space technology. So we'll discuss these questions first when we come back tomorrow, and then we'll start with space technology. So, right. So any question, anyone? Is half-life calculations important? Not for you, not for the examination. It is, I was just theoretically just know that this is how we do the calculations. Where these stages are held? No, these stages are not held. I mean, these are three stages of our program where we have this entire program, and this is what the program is. That first we'll do this, then we'll do that, then we'll do that. So now we are doing what? We are using the pressurized heavy water reactors. What do we plan next? Next plan is to use the fast breeder reactors. What's the next plan? The next plan is to start using advanced heavy water reactors for using thorium. So that's why stages, stage of the plan, right? So when you, for example, when you make a plan to study, first stage is to attend the class, second stage is to revise, third stage is to practice. Similarly, you have these three stages. First stage is pressurized heavy water reactors, second fast breeder reactors, third advanced heavy water reactors. What is half life? Don't understand. So again, I'll explain this. In half life, what I'm saying is that this is the time in which a radioactive element will decrease to half of its original size, or let's say original mass. Why? Because alpha decay is happening, beta decay is happening, gamma decay is happening. So you are losing particles, right? So any radioactive element keeps on losing these particles, and because it is losing particles, it will keep on decreasing in its mass. So the time that it takes to for it to decrease to half of its original mass is called as half-life. Why geothermal power plants are associated with induced earthquakes? What are the reasons? So basic idea is that geothermal energy plants, if you look at the entire world distribution, you'll find that all the geothermal energy power plants, they actually are areas or located in the areas which are along the tectonic lines. You have read about tectonic lines in geography, that how these are the fractured lines along which the tectonic movements or the plate movements happen. So these are always the areas which are the most prone to earthquakes, right? So geothermal energy areas will, you'll see that they also coincide with these fractured lines or these tectonic lines. That's why geothermal energy is always associated with earthquakes. I hope this clears that out. How many hours of sleep is sufficient in a day? Ideally 8, minimum 6. What is the strategy you give for target 2027? See, the target is simple. First, complete the classes, revise these classes as much as possible, and start preparing for your optional as quickly as possible. That you do a comprehensive study of your optional subject. Make sure that there's no stone unturned in preparing for your optional subject. And once you are 15 months away from the exam, start preparing for current affairs and start adding those current affairs to whatever you have already studied. Radioactive elements list, through with the ARMs, I'm sure you will get it. What is meant by octane rating of hydrogen with regards to HCNG? Octane rating basically talks about the efficiency. All right. Octane rating is always associated with the efficiency, meaning how much of material is getting converted into energy, or how much of fuel is getting converted into energy. That is something that is denoted by the octane number. So, for example, let's say if you see the advertisements of petrol, diesel, etc., you'll see that they talk about high octane petrol, right? They talk about high octane petrol. So that high octane, when they say octane rating, is always associated with the efficiency of the fuel. So that's why high octane rating in this scenario also means the same. If I start preparing from now, can I attend 2025? Yes, of course, you have enough time for it. Is any batch starting for 2025? Already started. I think last month only, February, we have started with the new batch for 2025. Who will take the art and culture webinar? I'm not really sure who is taking, but maybe because as a history faculty, we have a couple of them. Soumya ma'am is one of the history faculties that we have, yet she hasn't been taking history optional yet, or I mean, history webinars yet, but she is a history faculty essentially. My sleep reduced to 4 hours after seeing the syllabus. Now it's more than 1 month. Uh, See, I do not advise this because somebody who's well slept will be able to prepare well. If you are tired, you take more time to prepare. So the time that you think you have saved, it actually becomes counterproductive in many cases. So that's why a proper at least 6 hours of sleep with 4 hours of deep sleep is very, very essential for well-being of your body, so that your body can carry you through your preparation. Hmm. How carbon dating is done? See, it's a long process. You do not need to go through that. You just know the basics of it, that this is what we do and this is the basic concept behind carrying out uh, the process. What is the term unconventional form of natural gas? See, conventional form of natural gas is where you are able to directly get it from the oil, oil and natural gas refineries, or rather the reservoirs. So in case of coal bed methane or methane hydrates, all these are supposed to be unconventional sources, because these are not the sources that we naturally have been using, that where you directly have, just you have a reservoir and you are directly getting natural gas out of that reservoir. This is where you are indirectly extracting natural gas. So that is why these are unconventional. All right. Operational issues, some of you have written about some of the problems that you've been facing. If let's say you have issues that are not resolved, if you want, you can send those emails to me directly as well. I'll try to get those issues resolved. This is my email id, rashesh.kumar@byju's.com. Why Mukesh sir, Sham sir, other teachers left? It was their choice, they left. That's okay. They are wonderful teachers, no doubt, but that was their decision. What is my age? Why would you ask my age? I just turned 17. Okay, so let's end the class here. Please go back and revise. I know that this is a difficult part of the module. It will need your revision. So please go back and revise. And if you have any doubts, please bring them back tomorrow and we shall discuss them. Thank you.